Guys, this is Craig DeForest. Yeah, no, no, I'm masked. I know. We requested. I gotta go to Puerto Rico next week for another event. And I don't want to miss it.
No. Thank you, man. All right, this is your slides.
All right.
You have Max.
He does. I have a Mac. We work on PC. My Mac is my PC.
Which one are we dealing with?
There's a Mac.
Well, no. I can airdrop them to you.
Oh, you want to get? This is the thing too. Docs and the scientists, they're Mac users. This is the 6 years. I've noticed this.
Oh, yeah.
A lot of our Mac users.
Did they not already send your presentation? We have a whole bunch.
To it, but they were having trouble downloading it.
Oh, okay.
You have it on
This? Like 3 or 4 times. Security theater.
All right. Good for you. So you run that there, the safety
Yeah.
or something. Something. No, I don't. You have a knife. You need to wiggle.
Cut something. He's a wiggle.
Oh, come on in. He's gonna.
Or whatever. Let me put it on here.
Okay, fantastic.
Let's go.
Well,
Not bad. It's, I'm sorry.
my name's Nick. I don't know if we introduced ourselves.
Yeah, I'm Joe.
Nick and Joe.
Yeah.
Nice to meet you both.
Joe.
Great. You guys work for CPAESS?
We work for, I work for Spectrum Audio Visual. And Joe works for Spectrum Audio Video today and tomorrow next morning. He's a freelancer. So he works for himself and us today.
Sounds like you guys are right on top of it.
Well, I think we are now. Like anything, there's a little always hiccups on the first day of anything. Nothing we no showstoppers.
Yeah.
I'm going to handle it.
Good.
Oh, she's shaking.
Batman Wolfman.
It's what? Oh, Batman Wolfman?
I'm reminded of the first time I copied this on a Linux machine. Super floppy machine. Do you remember floppy?
The floppy, I remember when they were the 5-inch or whatever, and they were floppy, and they went to
3 1/4. So put the 3 1/4 in the machine, said copy my files over to my friend. I said, okay, I'm done. I said, all right, now eject the disk.
Yeah, you want to check your slides?
Yeah.
Second, Fang?
So that's happening now.
okay.
Okay.
I remember these. I am right on that edge of where technology.
Everybody's still naming differently after all that description.
As far as sound and audio is concerned,
Okay, so.
Oh, really?
Which is before digital, audio workstation.
Is there a particular slide?
Move back.
Oh, there it goes. Yeah, that looks good.
Oh, yeah.
Yep. Yeah, yours look great.
Yeah.
Okay.
Oh, yeah.
There you go. There you go. All right. No problem.
Oh, gosh.
Hey. See it, sir.
Well, we record 1,000 programs I think in at one beat. And then our particular plant had 3 or 4 cassette booklets. You can manage it, keep it all going. One guy can do it if you're focused. I think you can kick out 5,000 in an hour. By yourself. She had a couple people. And then once I pop one in, listen to it all, that's good. And thing, fast forward, we wanted to make sure it was something. I'm glad I had that experience.
Kids.
I call myself a kid. I've had experience. You know,
My son right now is doing film. I'm shocked by how easy it is. He used to record everything analog. Your scene could only be a certain number of minutes long, and you sync right because it ran at different speeds.
oh,
All right, is it the DeForest?
That's the one.
Okay.
I remember. How's the audio guy about this? I have that machine. We did have wow, this is working. And okay, awesome.
Right. Hitchcock used that technology.
Kids have so easy these days. I've become that guy.
Is that working okay?
Let me open it up real quick.
The problem with PowerPoint is it's not very PowerPoint compatible.
Is you're on a Mac?
It's PowerPoint. Oh, yeah, all my fonts are wrong.
Oh no. So let's
Are you
see.
showing it on this machine?
Yes.
So, would you mind? We could edit just the title far up there, just so that doesn't roll over. The punch mission should be one line.
Gotcha.
You could put it in Arial narrow bold. That would work.
Okay. Where is that at?
Upper left there, the DIN thing. It says DIN condensed. Just make that Arial and then pull it down to narrow. That'll be fine. That's cool.
You go a little bigger.
I brought a laser pointer, but I don't.
Yeah, that'll work. Thank you.
No, I was hoping I could.
Does that look good?
I have a.
That looks great. I appreciate it.
Not today. Mine is tomorrow.
Oh, okay.
All right, let's double check.
We have a video.
Okay.
Yeah, maybe can you talk with him on the break
Yeah,
while
that
you
looks
work with
good.
today's stuff?
We can just flip fast.
Yeah, on the break. That would be
Fantastic.
perfect.
Thank you.
No worries.
Let's make sure that movie plays. How about 2 up?
And you're muted
One
here
more?
in case there's audio. Do you have
One
any
more?
audio in your videos?
Right there.
Or is it just animated?
I think it might
Just
need to be in.
If you don't mind just trying to
Yeah.
show it, see if it runs.
Which one was it again?
Oh, that's one.
Yep, that's
that should be fine.
Okay.
That'll all run then.
There we
Yeah,
go.
that's
Cool.
the one.
On and then.
Awesome.
So I think we're good. There are a couple weird fonts at the end. Let's just quickly make sure they line up okay. I see that a lot of them are. That looks fine. Let's go up. There, that looks fine. Good. Okay.
Okay.
Now, do I have control over this thing?
You will have a clicker.
Okay.
Yep.
Right on. Thank you, gentlemen.
Yeah, no problem.
Joe. All right. Excellent.
Most excellent.
That's good. I'm gonna turn it off. Just
I'll take my thumb drive back.
Oh, yeah.
Good call.
It's right here.
I was going to sell it, but now that you're on it,
Thanks, guys.
you're welcome.
Of course. Nice to see you, Craig. Oh, we have something for you.
Oh, shit.
To keep you warm in the room.
Oh, awesome. This is great.
Yeah, especially yesterday. And I was like, oh, I'm glad we got everyone's
I
car.
like to cover my microphone so that I like to remote up in the studio where I like so much dust.
Yeah.
I don't like putting them all away. It's just a lot of work.
I wanted to ask, like, if my videos I can give
If you're what?
videos.
Oh, videos? Which slide is yours?
Sardana. Perfect. That would be amazing.
Try to bail out.
We found it.
All right, here we go. I'm going to make sure your videos play here. Do you know what slide?
Yes, this one. So it's a YouTube.
Oh, this one is?
Yes.
Okay. Yeah, let me see.
It says controls like
Should,
It looks like, oh, that's the slideshow.
it should play once you advance the slide.
Yep.
It's just fading in. Oh, here we go. Let's see. Hyperlinks can be harmful. Oh, here we go. Oh, now it's opening up a separate.
Yeah, she said it was a YouTube, so it'll launch that. But that's great.
I thought it was going to play it in here. Anything else? No? Okay. Let me recheck the links. I guess I could. Won't let me edit the link. Just
turn the
open.
background music down. It takes a
Oh. I am not seeing it, but I will try to open it for you when we go.
Okay. I have the just video format also.
Okay.
It just Google Slides wasn't allowing me to upload, like it asks you to upload on something and then use the link.
Yeah. I will try to have these queued up, and we'll just have to switch between and plan.
Yeah,
Yeah,
that's what we'll have
because
to do.
it's like really important. The video part, they're like 1 minute videos.
Okay.
Yeah.
So
If we can-
I'll try to queue them up here on a tab.
Let's take our home slide.
Oh.
Yeah. At least they want to start on time.
I hope you all had a fantastic night's sleep. It's already there, so I think we're all feeling much better. Welcome back for day 2. I do have an announcement to make. We have been made aware late last night that one of our participants came down with COVID. So I do want to let you know to please take care of yourself. Everybody that was in close proximity to our participant has been notified one-on-one already, so they have been notified. If you have not been notified, you are not in close contact with this person, please take care of yourself. We have masks at the front desk. We can get more if you need. If you need anything else, please let us know and we can help you to take care of yourself. So, and as we get information, Kate will share information with me, and I will let you know as much as I know when I do know. So apologies for that, people. It happens. CDC said we can carry on with our lives and just mask and carry on. So that's what we're going to do. And I'm also going to say very thanks to Mike Little for taking the chair position this morning because Ankush is still stuck in India. So thanks for stepping in, Mike.
Okay, so I'm going to apologize in advance. I know you're not supposed to do this, but I'm going to anyway. For every time that I mispronounce somebody's name, so just stand by. It'll be considered entertaining, and it might turn into a drinking game. That is, you drink when I actually pronounce it correctly. So anyway, so we're going to start this morning for about 20 minutes to talk about the previous day's working group session. And so, Gavin, oh, okay. So if you come up and sort of give us about 5 minutes.
Minutes is a little more than I actually maybe, but 75. What we're looking at is making things a lot easier for people, researchers, to access a lot of the solar data.
for climate purposes. This is a cross-disciplinary and field program we showed yesterday that people who are working in climate don't want to have to know all the details and nitty-gritty of solar irradiance or sunspots, but they would like the easy access, seamless access to the data. And using a model, the NASA VDAC model of open source simplicity for being able to get to data is a role model that we want to follow or build on. When it's much broader, the analogy we had was going after just solar aspects with killing flies with a sledgehammer. But the neat thing about that approach is it's very expandable. We're looking at this as kind of heliophysics, getting solar more into climate, but it needs to be broader than that. We need more than just solar aspects. We're eventually going to need, by the way, the PETA is going after greenhouse gases, which is a major part of climate. We would like to add in solar to that, and we can do that through heliophysics. But ultimately, we need a lot more. We need aerosols, we need oscillations, normal weather patterns on the earth. We need to do a lot more than this. So solar is kind of our stepping stone to get things expanded a bit. But we would like to head that direction with a proposal through geophysics, building on the model, just like solar. That's kind of the gist of where we're going. Starting to put together a proposal to that end. That's probably it for next.
Yes, thank you, Dr. So plan today, just to say, how do you use space weather? So who's speaking for space weather? Oh, yeah, of course. No.
Hello everyone. So yesterday I will talk about science methods in space weather, and so we started with about the existing methods, groups, communities that exist that are doing science, and whether it's in the form of websites or data sets. And then we talk about what are the limitations that exist if it's reaching all the people all over the world. And if, let's say, the website is there, but it's not user friendly. So we discussed, we walked through all those issues, and we came up with a few approaches. So one of the approach we talked about was developing a website where people can upload their data, but then how to make sure that it was not everyone. So this was about engagement and not just about the program, also with other ideas such as what about the use of social media, or what about the use of TV channels, and about sandbox approaches where people are using or developing 3D tangible models and doing that open science. And the other thing that we talked about was emerging technologies such as AR/VR approaches. And so not just talking about the scientists or the general public, but also defining who are we designing for, who the general public is. Are we talking about the students here? Are we talking about collaborations where us as scientists can collaborate with the data scientists or the coders and ways to teach them? So it was all in this brainstorming design phase, and now we are thinking of putting together a proposal of how we can do science in this space.
Sat there long enough, you have to do a bonfire, so exoplanets is next.
Hello, everybody. My name is Vladimir Vijan from NASA Goddard Space Flight Center at American University, and I had the privilege to work with the 6 really great team members, the scientists that basically cover diverse fields that can be directly applied to understand exoplanetary environments, including Manji, Shinal San, Omkar Pascal, Lisa Winter, Aiyun Ling, and Tiffany. So we have diverse experiences in diverse fields. One way that we want to start to address this question is that we're living, in this revolutionary era when these over 5,500 exoplanets have been discovered, and we're moving from the era of discovery of exoplanets to the atmospheric characterization. That's where the heliophysics tools come into place. And so of course, the one obvious way to address those issues and to make a sizable contribution with the group will be to move from our sun to solar-type stars. Because we understand that the sun is the best star we understand and the best star we can model. So therefore, we even though we have over 3/4 of the M-dwarf stars, they're pretty crazy worlds, we have plenty of stars. 10% of those stars in our galaxy are solar-type stars. So maybe we can start with the obvious cases of exoplanetary systems that host planet-hosting stars and exoplanets around them. So therefore, we identify the three major topics that we're going to work in the open science. It's first to work with the existing catalogs to identify the young solar analogs, so where we have some cases, even though we have so many tens of thousands of stars, 150,000 stars observed by Kepler. We only have a handful number of solar-type stars that can be that close by, that can be observed by the Hubble Space Telescopes and XLM and other missions for the characterization of their ionizing radiation. As we understand it, ionizing radiation environments are very important to understand the climate, stability, and just atmospheric environments of exoplanets. So basically, the second the item will be the data to develop the data constrained MHD models of X-ray and extreme UV emission, the wind, and the characterization of superflares and coronal gas ejections, the obvious the high impact sources of atmospheric evolution. And the third one is, and of course, identifying the models that we're using and describing these models and identifying the limitations of those models. And the third item is atmospheric escape models that we currently have in place that already apply to understand that the escape of oxygen and nitrogen from our Earth during solar flares, but also to enhance them to the exoplanetary environments. And the last topic will be to eventually apply all these tools, and not to say chemistry tools, in the interaction of SCPs with the exoplanetary atmospheres, eventually to apply those tools in order to identify what kind of signatures, high impact signatures, high signal signatures we can find for this upcoming observations with JWST, because our final goal is to develop predictive science. And so It looks like that our goal will be to write a white paper to address all those issues and to see that where we are at this point. Thank you very much.
So the next talk will be by Jennifer Gannon, who's the Vice President of R&D at Computational Physics. And I have to say, the title of the company is one of my favorite titles in the world. I mean, just think about computational physics. It does, yeah. Thank you very much. I'll give it a number.
I'm bringing my coffee because it's a little cold here. It's kind of climate change I like. So I'm going to talk about data today. Got my slides up. Everyone want to use these things. Does this have a back button? The red one's a back button. So I'm going to talk about data today, which is something that is extremely powerful in science. The foundations of most of what we do is space weather, and I'm going to specifically focus on ground-based data. So I'm going to start off by saying something that you may not agree with, which is that ground-based data is kind of maybe a little undervalued, a little less popular, not as cool as some of the space-based assets. That's a little bit of the shame because there's so much history in ground-based data, and so much of the ground-based data goes to support a lot of space weather indices, understanding the modeling, and it is just critical to what we know about space weather impacts. The positive way to put that maybe is that there's so much exciting space-based data that we're just kind of a smaller part of the toolbox now. But as that shift has happened, a lot of that ground-based data is moving to the commercial sector, to industry. And that comes with a lot of opportunity, a lot of new sources of data, and some complications for data. So I'm going to talk about that a little bit. I'm going to use a power grid example from a storm from 2021 to G3. And the analysis of this event would not have been possible without a new source of open data from the power industry, which is a database of GDC information. It's been really, really useful. So, first of all, in this shift of a lot of ground-based data going to the commercial sector, or use of a lot more commercial sector data, one thing hasn't changed is kind of focus on extreme events, the big grid-killing, end of the world kind of events, because that's something that we want to avoid. When we talk about space weather and space weather impacts, that sort of makes sense. There's a lot of really, really good science in moderate and small events, and that science can lead to better understanding of the extreme events. So as we move to industry, that really hasn't changed. The power industry also is looking for these large events that we're trying to measure for large events. So most of this database that I'll talk about is really focused around storms. We don't have a lot of quiet time data. It's storms that are KP7 or G3. So the event I'm going to talk about is May 12th to 13th, 2021 geomagnetic storm. It's a little bit of a boring event. I mean, it was a nice event, but it wasn't exciting. It didn't move down anything. Power grid, no one died. It was kind of a typical normal G3. It was super exciting to watch because it was one of the first G3s coming out of the solar max, and we had some activity. But the event itself wasn't that exciting for the power grid. However, we had this new wealth of data in our UCAR database. So I'll get into a little bit of the history of how that database came to be. But we had a lot of GIC measurements from the power grid that we've never had before that we start to look at about this time period. And we picked up this event, we looked at it, and we saw this time series. So this is measured current in a substation in a transformer just outside of the DC area. So measured GIC data, not model, not magnetic field, measured current stored through the power system. And there's a couple of interesting features in this storm. So first of all, there's a peak of 30 amps per phase. Again, not catastrophic. Power utilities don't really get concerned until it's up to about 75 amps per phase. So this is maybe half the size of what they really be looking for. And it's followed by this 3 to 4 hour period of heightened GIC. It's not the same level, but extended periods of GIC that can cause different kinds of issues for the power utility. So that really caught our attention. What could cause this kind of extended GIC? Could it be bigger? If it could be bigger, that could be really bad for power utilities. And this is right outside of the DC area. We really weren't expecting it. So it was a weird event. And because we had all of this open data in this GIC database, at this place in Fredericksburg, this one substation, I think there were 20 or 30 measured storms that we measured for fiber mile. Just opened this database up. We looked at the history of other G3, G2 storms, and this storm was just different. It was so much larger than anything else that had been measured at Fredericksburg. So again, it was a clue that something was different. It's something that we needed to understand, because if you create these kind of conditions during a moderate event, what would it take to create these conditions during a moderate event? So these are some other measured GICs in that location outside of D3. Okay, so let's get into a little bit of the history of the GIC database. So for those of you not really familiar with the GIC history, I'm sure everybody's heard of the 1989 event, which caused such problems for the Quebec power system. There was a power failure. At the time, nobody attributed that to space weather. They actually blamed the power utility. But this whole GIC thing began around that time. We realized that there would be power impacts. It took about 10 years after that for it to become really well understood that this was a space weather effect on the ground. Because of that, the government, for Federal Energy Regulatory Commission, directed NERC, which is a consortium of power utilities, it's a corporation, it's made up of power utilities, working in the interest of power utilities, to assess the needs for mitigation for space weather and really to kind of self-regulate, to put together their own set of rules and mitigation procedures to prepare for space weather. And that's called TPL 7. So that's a federal regulation that directed the power utilities. So as part of TPL 7, power utilities had to do a bunch of things. They had to assess whether they were vulnerable using a set of really kind of simple criteria. And if they were vulnerable, we wanted more stringent criteria. But it also directed them to measure, to take measurements of the magnetic field or to use measurements of the magnetic field. They didn't have to do it themselves. They had to have measurements of the local magnetic field, which drives the GIC, and they had to have measurements of the GIC themselves. That's where the regulation stopped. It just said measure data, full stop. It didn't say how much, didn't say when, didn't say what to do. And so it really could have just kind of died there. And it didn't. So recently, maybe in the past 5 or 6 years, there's this data request. So NERC put together this data request to the power utilities and said, okay, you've been measuring this data, and power utilities are concerned about GIC, so they put out more than just 1 or 2 monitors. They put out hundreds of monitors across the US. I think there's, for each storm now, there's probably 700 monitors that are recorded for each one of these storms. They said, please release this data publicly. And this has been a long battle, a long kind of, at some point, uncomfortable conversation about getting this data, GIC data for a long time. It was really, really hard to get unless you could go work with the power utility and sign an NDA and they trusted you, but only you could use it, you absolutely could not publish it. This was a big shift. I still don't really understand why they what shifted in the culture or in the partnerships between researchers and the utilities, what shifted when they made them take this leap of faith to open up their data, because this is voluntary. It is a voluntary action on the part of the parent. Well, it's been, it's a measurement of vulnerability in their system. So they were concerned that it would point out where they were weak. They were concerned that it would bring more regulations down on their head. They felt they could handle it internally. They didn't want the regulation to come in and cost them millions of dollars. So, but they also see, a decade of science coming out that really helped them. There's science that they didn't have time to do. So I think that's probably part of why they do this data. It's just it's been a wealth of information. I would just start with the data into it's all out there. You should all go look at it. There's two GICs. You can hurry up and see. Okay, so that data is made available. So for those of you who are not GIC people, what we usually look at when we're looking at the drivers of GICs, or we do a big CME, those are the costs of the biggest GICs in the power grid. CME impacts the earth, so you get a big reconfiguration of fields, you get current systems and all this stuff that you guys already know about, and that drives a varying magnetic field on the ground. So like what you say is like the magnetic field is the driver of GICs. The magnetic field then induces an electric field at the surface, and that electric field induces a current in anything that's a long line. So the magnetic field is really important. So the next source of data I'm going to talk about is magnetic fielding. Magnetic fielding is critical to understanding GICs. And you have to have it kind of locally. So can I go back to this previous slide? It's a reconfiguration of fields, but it's a reconfiguration of fields to change a DPDT in the presence of a non-uniform conductor, which is here having that a little bit too. So it's a complicated E. It's not just a B in a vacuum producing a perpendicular E on the surface of the Earth. It's a lot more complicated than that in space and in rotation. So you need a lot of magnetic field data. So this data, this is a magnetic field, a magnetometer network run by CPI. It's been funded by NSF for about 5 years. We're extremely grateful to NSF for continuing to support this network. We work closely with our utilities. And they regularly use this data and work with this data for having the local measurement of the magnetic field. So we had magnetic field data. Because it's funded by NSF, it's publicly available. And we've been trying to make sure that it can get out to as many people as possible as well. So we have this, and we can see from the magnetic field that there was a remarkably uniform variation in magnetic field across the US. So these are a bunch of different locations in the US, from the West Coast to the East Coast. During a GIC event, you often see the magnetic fields kind of chaotic, in particular in orientation, which causes some of that complexity, some of that local complexity. But we saw that something was really surprisingly across the US on this measured data. Okay, so I said the Earth is a non-uniform conductor. Vary's law, change in B, induces an E. It's in the presence of the this non-uniform conductor, which is the Earth. So that has a couple of different effects on the electric field. Very sensitive to frequency. So because the Earth has different conductive layers, the mantle and the core crust, which have different properties, the electric field that is induced at the surface is a function of how deep the magnetic field can penetrate. So that skin depth of the magnetic field means that it goes to different depths into the Earth, which means you get a different frequency content interacting with a different level of the Earth. So we've got a frequency content dependence on the magnetic field on the GIC hazard. So you got to have highly resolved magnetic field. You can have one cycle magnetic field and really get the full GIC response. But it's a little more complicated than that. There's also non-uniformities in latitude and longitude in space. So mountain out the window, there's a bunch of mountains out there. That's a big conductivity structure that's different than the plains. So it's different laterally as well. So it's not just varying with frequency because of that depth, it's also varying by location. And the more complicated the conductivity structures, the more complicated that Jackson E&M probably becomes an induction E. So you get E pointing in a bunch of complicated directions. So you get a lot of less lovely. Again, we have lots and lots and lots of data. This is from the University of Oregon EarthScope project, again, NSF funded. So NSF funded this project to march across the US, measure conductivity on a 70-kilometer grid. I forget what the original goal of this project was. It wasn't GIC specific, but wow, it became really useful for GICs because it's really going out and it's mapping how the local hazard changes in the 70-kilometer grid. It's giving us a bunch of data to do this investment in this population. So again, NSF funded 30 universities. This is not private sector. Really open for errors. Okay, so from this MT data, we can know which parts of the US have the highest GIC hazard. It's upper Minnesota, which has a really high area of GIC. And this part, it's not color coded, it's kind of like random color coded. Unfortunately, the numbers that you probably can't read are the relative hazards. So it's a number relative to the hazard in Quebec here in 1989, which is maybe a little bit arbitrary because it's all started in Quebec in 1989. That's our reference. So a higher number is higher hazard. So upper Minnesota is 2.7, which is fairly high. Maybe you can see the effects in some of the GIC data coming from there. And in Maine, Maine really has a unique situation in terms of GIC in the US because it's got a really different geological structure that's coming on. I'm not a geologist, but it's basically glued onto the US through some of the processes over time, and it's made of a different kind of material, and it also has a strong coast factors. You get a difference in connectivity between the earth and the sharp drop off into the water. So Maine has a very high response. I think it's a 3.5 there, 3.3, and then all along the application range, you get like 4.2. So maybe DC to New York. DC to New York is that high hazard corridor. And there's a bunch of reasons in the middle, like here, we don't have that much of a response. Even if it's flat and open and sandy, it tends to be a little bit less hazardous for you guys. Okay. Yeah, it's the lakes don't contribute as much because they are but yeah, they're freshwater, but there's also again I can't remember what it is. There's that blade of material that comes down from the Canadian shield. The same reason that the back has the high hazards of this they got a blob of material deeper connectivity structure that takes it apart. And it is very isolated right around the Minnesota area. And there's some really interesting transmission lines to that region as well. So it's a good region to study. So from this data, really important data. Other areas that are particularly complex. I mentioned this New York to DC and Maine and Minnesota. So each location, the more complex it is, the electric field isn't going to point in the direction you think it is. The B is primarily north-south, but it's moving all over the western storm. In these complex regions, the E may not even vary in orientation at all. It may be fixed just because of the nature of that connectivity structure. It has a preferential orientation. And sometimes that preferential orientation is a really disadvantageous location with relation to a power line. So you have an E like this, a power line like this, that's maximum GIC. Sometimes it works out really well, E is like this, the power line's like this, they really rarely see anything. That's kind of the case in this DC site that I'm talking about. That's why you rarely get the GICs at that location, is that the E is typically perpendicular. It typically doesn't really align with our grid structure. So we got a lot of complexities, and the data really helps us to dig into what this is. Okay, now we get into the political complexities. So you've got E pointing in all sorts of directions. You've got this all changing with time. You've got the conductivity response creating a lot of this variational hazard from place to place. The power system is an incredibly complex machine. I did not understand this as a manuscript scientist going in the GIC world. This is an incredibly amazing, balanced, just complex miracle of human creation. And the fact that people can, so many people get together and keep this thing going and keep it, keep the power on in such a consistent way is really, it's really impressive. Because the power grid, and you've got all these different lines, pointing different orientations. Each interconnect has to oscillate completely in phase. They've got to balance the generation, the input, and the output. So people turn on all their ACs at once. And it's just an incredibly complex process. So when you're trying to look at GIC hazard, you're taking something that's already kind of physically complex, like electric field, and mapping it to something that is structurally complex, which is this highly interconnected power system. Not only that, there are a lot of parameters within the power system that affect how the GICs get reduced in lines. So the substation, how is it grounded? Was there rain water that day that changes the grounding? How long ago was that substation put in? Because that grounding is going to corrode over time. That makes a huge difference. What's the conductivity resistivity of that long transmission line? What are the voltages of the step up, step down transformers? Where do those lines go? We tend to map them as straight lines between points because that's easy, and we don't have the rest of the information, but they don't. So what if one of those lines goes around the mountain and through an area of high electric field, and not necessarily, over the mountain, right? Like that straight line distance seemed to imply. It's very complex. There's a lot of data and information. This is all owned by power utilities. So there's a lot they do with these models. It's a lot more than GICs. GIC is simply small add-ons to this. We use this to balance load, to model their systems, to see how they should respond to all sorts of different kinds of changing inputs. And there's a lot of proprietary sensitive information in there that's also needed for the GIC calculation. So this is where some of the GIC data becomes more difficult to access, but it's also where a lot of really good science is being done. Because you want to connect the driver to the actual impact. And if you're going to really use this GIC data, this availability in your database, it's pretty important to make sure you're doing a realistic grid, which means working with the power utility or working with the grid partner. Doesn't mean you can't do anything with the GIC data and so on. There's a lot of good science that's being done without using the full grid. This is really the way to get to that the true estimate that you have. Okay, so what do the power utilities do with all this? They do what's called a GIC model validation assessment. It's assessment of their models and of specific models. So they've been told to measure the magnetic field of GIC. They extensively have that. They take that electric field. They take the magnetic field and calculate the electric field using a conductivity model. So it's really simple. I'm getting more complex just to describe this whole process. They take their system model and they apply this electric field to their system model and they estimate GIC in their programs. Okay, as to the GIC, Somebody smarter than me could come up with that probably. But one of the benefits of the ground-based data is it is cost effective, and they can go and they can move these instruments around as conditions vary and as they need to leave them longer or shorter, or retake data or go fix an instrument. So I think it's most countries that I'm aware of are doing it from the ground. But I don't know. Interesting question. Oh yeah. There's the right answer. Yeah, that's the right answer. That's the correct answer. Satellite-based soil moisture, because we need that metric of soil moisture to get to the next step of accuracy in GIC. Yeah.
So, following on the theme of open science, one of the issues that at least we used to face was getting information on space weather effects out of commercial entities and even out of parts of the government, whether it's for competitive advantage reasons or security reasons. Is that still an issue, or are there ways to deal with that?
I'm going to go back to that trust and relationship building. I think the reason I like this event so much for this forum is that this data wasn't open for a long time, and it is open now, and it's extremely valuable. It's extremely valuable to everybody, but it really did take a leap of faith from the power utilities that it wouldn't be used against them. And so I think it comes back again to that relationship building and that trust building with the end user and understanding the needs of the end user. And this is a success story. This could be a model for how other industries do it.
Thanks. Once again, excellent talk. You keep hearing that from all of us. I had to jump in. Earlier you said, I don't know why these people open their data.
Yeah.
And that drove me to comment, especially for the younger folks in the room. We owe almost everything good that happens in the field to somebody who had a wild idea and saw it through. In this case, we owe a lot of thanks to Ernie Hildner, who ran the Space Weather Prediction Center for a long time, for really lobbying folks to open this data. People like Bill Wagner and Alan Teitel from NASA, who opened up the NASA side. The comment really is, if you see something that would be great for everybody, pick up the phone. Make some phone calls, try and build those relationships and make it happen. These things don't just happen, right? You make it happen. And we're right now reaping the fruit of seeds that were planted 20 years ago. So
it didn't happen because there was a federal regulation telling them to. It happened because there was a request and they trusted the person who made the request. I don't know in the end, who it was that really pushed it, that final step. Like you said, there's a lot of people that have been trying to advocate for it for a long time and done a lot of good for the GIC community and for the power grid community. But yeah, relationships, trust, and pick up the phone and make a friend and try to understand where the power utilities, what their needs are and where they're sitting and what they're thinking.
Over here. Hi, Jen. Question along the same lines. So this situation of trust can be quite fragile. So I wonder if there's some sort of protections that can be put in on the data usage so that these companies aren't faced with these billions of dollars of unfunded regulations. Don't get me started on the unfunded, because that's a problem in itself. But I wonder if there's some sort of protections that can be put in. What would you recommend?
There are, so I think looking at the data request, it was a request. It was optional. That made them feel more secure. Like it was, they were being able to make a choice. They were also allowed to downgrade the location information, which is one of the things they find most sensitive. So the lat and long pair is they don't have to give the full latitude and longitude. They can give it to 1 decimal place, which is good enough for most of the grid modeling work right now. On some of the grid models, I think there's a lot more that could be done to separate the sensitive information from the stuff that we do just for GICs. The GIC data really, that part of it isn't that sensitive. It's the rest of the grid model that comes along with it. But that takes time and effort. The power utilities,
in terms of funding, if it's under a regulatory mandate, they can pass that cost on to the consumer. So they can pay for it if they want to, and if they feel that there's a need for it. Again, I think it comes back to building that trust with the end user and understanding what they need versus what we need, and making everybody win. Everybody's got to benefit from that large amount of work that it would take to separate the sensitive from the non-sensitive. But I think it's doable. Yeah.
So we have time for one more question. Anybody else want to take a shot?
I have another comment, and it's a more cynical comment, because it has been a very positive interaction here, that you have a measure of trust with these companies, and you have an interpersonal relation that makes them give you the data and lets you use it. But I'm thinking of this packages, come up with stuff, and then now they can leverage on all of the stuff that's been done by the public for their own benefit. So if you're getting something for free, you are the product.
Yeah.
You are being brought, basically. So there's something else. I mean, let's face it. I mean, a lot of these companies exist to make profit. They're not here for charity. So I think, I mean, it's nice to say that they trust us, or there's some great brotherhood that's going on, but I would still be very cynical as to, okay, what are the general aims or what are the general requirements from your side that need to be satisfied, let's say not now, but in 20 years or something, which the community will eventually come up with, because once the data is made public, you have innovation coming from everywhere, right? So this is just a thought I wanted to put outside, and maybe have your comments on what you think about this.
Yeah, I think it's a great point, and it gets to what that data sharing can really provide. I mean, the benefits to both sides, spurring the research, which will then help the power utilities. I have an optimistic view that that's why they released the data, that they started to see some of the benefit of the science working for them and making their lives better and showing them where their vulnerabilities were. And so they said, okay, we'll release a little bit more and see where this goes. And hopefully it snowballs and we get a lot of data and they get a lot of benefit and we're all safe. I will say the power utilities, yes, they're corporations, but they're also made of a lot of people, and those people are not there for a profit motive. The people are there to keep the lights on because they love this beautiful machine. I mean, they are engineers that love the power system. So they're not that different from us as researchers. But I think that just that supports this idea that we can all win. And that I hope you're right. I hope we release it, and the benefit they get is from the science that comes out. Yeah, hopefully they don't sell our data like Google, but
Well, thank you very much.
Thank you.
Truly an excellent talk. One last round of applause for Dr. Gannon.
Thanks.
Thank you. And our next speaker is, and I'll apologize again in advance, Tzu Wei Fang. Close, anyway. And she's from NOAA's Space Weather Prediction Center. So take it away.
Hi, I stepped into the room and I realized I don't know many of you guys here. So hopefully I get to know you more today. I'm from Space Weather Prediction Center. I'm going to move this because I know it's So Space Weather Prediction Center is the official space weather center that issues space alert, warning, and watches in the U.S. And we don't just support U.S. sectors. We also work with international partners and to help guarding the whole globe. So typically, in my daily routine, I get lots of requests from customers everywhere in the world, even from India, from everywhere. And I asked my boss, is that my job to answer those questions? Like, well, the more impact you understand, that you learn more. I said, okay, so I take on more and more. And I guarantee you by the end of this talk, you're going to have a lot of questions follow our previous discussion in terms of open data. So Spatial Prediction Center actually outlook a lot of customers. So we talk about power grid, satellite industry, FEMA as emergency. We have a typically call with FEMA in a weekly basis. And, GPS impact on the agricultural GPS impact on the tracking, on the aviation systems, on the shipping systems with HF communications. So there are a wide variety of impact that we are looking. Sometimes I myself get overwhelmed. I have to really think about physics and trying to understand and translate that impact. And it's not an easy job because I think a lot of time we're all trained as a physics base. We're all trained with physics, right? Now I have to figure out how to translate that, apply physics to the customer, which is not trivial. So this is the latest thing that we're releasing actually last week. So I got a lot of customer complaint. Solar cycle already go halfway. And your solar cycle prediction is still like 2019. So we're going to do this solar cycle prediction plot and update it every month because there are a lot of need, especially the satellite industry has been complaining a lot, and they give a lot of feedback on how they want. And then they don't just want this 2032, they want anything beyond that. So last week we had a big engagement. I was like, I can't give you something beyond 2032, but they want just give a number and just give a curve and as official as you can because they need something. So if they need something, it's better to have a standard than no standard, right? So better have something for their lifetime analysis for their satellite and spacecraft. So this is a newer product that we are upgrading, just started releasing last week. Hopefully everybody from the community can benefit from the newer solar cycle prediction plot. So my background is ionosphere thermosphere. So I'm going to talk about the impact of ionosphere and thermosphere based on space weather. And my team at Space Weather Prediction Center have about 13 people. We take care of all wide variety of ionosphere thermosphere impact from HFCOM. And it's very important to understand the frequency range that can be used by the HF communication. We are very worried about storm impact, especially the Ukiah River storms. That's where the impact of the So there are different time phase of the storm impact different structures and impact different industry that we're seeing. And for satellite positioning, navigation, timing, and communication, we're worried about ionosphere changes. And a lot of times our customers don't even know what they're talking about. Like they're like, oh, there's something going on here, something going on. So that translation is quite difficult to start with from ground zero. But we kind of explaining what kind of structures we are looking for in the ionosphere, talk about why sometimes you use this parameter, sometimes you use that parameter because of signal degradation. We talk about smaller structures in the ionosphere. And a lot of times, a lot of those studies and research still in the research, right? So it's so hard to, I almost feel like every day what they're asking, I don't have it. Like that's kind of my daily feel is whatever customer need, we don't have it. Whatever they want, we don't have it. But what can we give them as a, just start with that and then see how it is. And if we don't give them now, they engineer everything around. So we are become involved in this research field. So I think that's very interesting feeling I got every day. And we started to do a lot with satellite industry on satellite drag for the neutral density, trying to understand the neutral density uncertainties. It's very important for them to understand when they need to maneuver, when the collision risk is increasing. Especially a lot of people are going low insertion orbit with constellation company these days. So drag suddenly become important in the past 2 years. It just suddenly, in the past 1 year, I feel like I'm riding the roller coaster as a scientist, like, oh, it's going very exciting and there's so much information coming in. There are a lot of companies are very open. I would say the space industry is a lot more open compared to a lot of industry we have worked together with before. So I'm not going to talk about HFCOM, it's just too much detail. I'm going to focus on two topics. First one is the ionosphere, because my team has built up a lot of products that we can support that ionosphere specification needs. And we're still exploring. A lot of times I also fact check myself all the time and say, why do I do this? Who cares about it? Why do we do this? Why do we do TEC? Who cares about TEC? And a lot of people tell me, we don't need TEC anymore. We have multi-frequency receivers, we have multi-constellations. And are we still doing science that is based on last solar cycles and trying to help our customers? So those are questions that we ask ourselves very frequently. So what we have been building is based on a lot of data, right? Again, we need a lot of data. And to get the ionosphere specification globally, we can't use ground-based. We cannot count on just ground-based data. So we use a lot of satellite data. So Formosa said Cosmic 2 is the NOAA, Air Force and Taiwan collaboration satellites is going on. We have 6 birds in lower latitudes, kind of giving occultation information of ionosphere. We largely leveraging commercial data right now. So NOAA is purchasing commercial data trying to figure out if we can use that operationally. So we take care of our center utilizing Spire data, Planet IQ data, trying to fill out the gaps that we don't get from cosmic mission. So polar region, high latitudes. We are also actually using this data to understand the impact of simulation. So using those data, we can really understand the signal going through the RO and how does that causing the simulation besides TEC itself. And we're also trying to utilizing large ground-based receivers. So we're trying, these are all free. So we are trying to get as many free data as we can everywhere in the world. And I told one of my teammates that you can just keep on adding data. That can be a whole year job. But again, let's go back and look at the requirement. Why do we want to add more stations? Where is the value added in? If you add 200 stations in the US, is that value? If you 200 stations in Brazil, is it adding more value? So I think we really need to think hard on that. But we want to utilizing high frequency receiver, low frequency geodetic receiver, just to gain that kind of coverage for all the atmosphere modeling. So using that model, we built a real-time nowcast model based on an IRI-based model, and that model capturing a lot of features that we don't typically see in a lot of empirical models. And then with the data simulation, you can try to capture more points where the realistic weather is happening. So this particular model was used to support our ICAO requirements. So we have a big requirement on space weather with the International Civil Aviation Organization. So we constantly issue space weather warning to the organizations so that the major airlines and pilots receive the space weather alert and warnings. And then using this model, we also can estimate, right, where do we need data from? Obviously, with ground-based data, we don't have anything from the ocean. So whatever you can see that the changes between left and right are adding more stations, adding more space-based data. So you can see that the structures in ocean has been largely altered. But again, sometimes it's hard to validate, right? We don't know what's look like. So, but building some of this system can tell us, what kind of stations we need, what kind of more data we need in the ocean area, in the polar region, so we can do a better job for particular customers. And then we also really worry about simulation. I have rocket company come to us and say, are you going to have simulation throughout my flight route? I said, I can't make decision for you. And they call 3 times and 3 hours, is that a go? I said, I can't tell you if you should launch a rocket for you. So I think there are a lot of interesting perspectives that when we didn't even think about. So I think it's very interesting because the space industry is so new. And we used to only need to worry about NASA, right? We work with NASA for their launch. We worry about NASA on their satellite. Now they're just launching everywhere in the world. And they have different equipments. They have different instruments on them. They use different receivers. And when they come to us, it's very difficult to interpret what they're looking at. It's very difficult. And sometimes, like they want me to sign, and sometimes they want me to sign an NDA, but since we're a government, they have decent trust. But they were like, and eventually sometimes they can't solve their problem. They show us their GPS receiver data. And then when we looked, it's all interference, really not space weather. So I think there are a lot of difficulty when translating the impact and ionosphere and space weather. So I think this is the other thing that we had a lot of customers coming to us to try to understand how these smaller scale ionosphere impact their signals. And from the ground-based receiver, we can identify S4 sigma phi as the strength of simulation. But with RO data, it becomes very tricky. You're going to 2,000 kilometers on that line of sight. And how do you identify, where is that simulation coming from? And how does that simulation look like from the ground, since people want information from the ground? So we struggle a lot trying to translate that information to serve our customers. So to do a better job, so since we can't do very good on one thing, so my approach is that just do whatever we can, just put everything lined up together and get to our forecast office. So we have the rate of TEC index change. So you can see those are from ground-based receivers. And those change in the kind of indicating how severe the simulation is happening. So typically when there's a space weather storm, we start to see high latitude simulations. And low latitude simulation has totally different physics. They're just there all the time. And with solar activity increasing, we just see that all the time. So should we trigger that or not? I mean, my forecaster asks me all the time. We see that simulation severe in Brazil all the time. So should we trigger the warning or not? Because it's just there all the time. So does it mean it's important to trigger it? Or maybe since it's there every day, then it's not important anymore. So I think there are a lot of questions we kind of never thought about as a scientist to start with. So we're trying to increasing more ground-based receivers. We're hoping to fill up our gaps. And we're trying to utilizing space-based data, trying to produce different levels of product that can be used to support the decision-making at the Space Weather Forecast Office, as well as for our customers. And then recently in 2021, our team released this whole atmosphere model and IPE model to operationalize. So the model currently have 2 different concepts. And when we built the model, it was a research tool to start with, right? We were curious how this model, so this model creating from the ground all the way to the space would be like similar to Wacom-X that is built in NCAR. So this model trying to capture the wiggles and wave coming from the ground all the way to the thermosphere and ionosphere. And then once we get this operated, I start to get a lot of call, over the horizon radar. We get a lot of customers are very interested in ionosphere changes. And suddenly from last year, we have to deal with satellite industry for drag problem, and this model become a top tier model that they're looking at. So we capture, like, for example, this model captures some of this SED features on the polar region. You can see that the plume on top of American sectors can well capture from this model in the forecast mode. So you can see that the impact that we received is really like, if you go back to talk to the FAA, they have this wild communication systems supporting GPS signal lost. Then they can also see that there's a huge, you see that blue, middle of the blue suddenly become all red, means that their vertical resolution has been degraded. So that is really just got to do with the ionosphere and that wall of ionosphere change impact on the single frequency receivers. So we can do some of this analysis afterwards or in a real-time system. I'm gonna skip this. So we start to work on a lot of exciting things, looking into the causal relationship, trying to understand how can I predict simulation in the future? Because that's what customer want. The customer come to us and can I understand tomorrow? Can I, I'm going to have, now they have autonomous tractors. So autonomous tractors going out tomorrow to see things. Can I know if there's simulation impact tomorrow night? And we don't have that. We just don't know the physics. We don't know the physics well enough to predict it. So there are a lot of things we can get, but we're trying very hard to see if we can kind of pinpoint what are we looking for so that we can give an alert and warning in the future. This just an animation shows how dynamic our model is producing in a system. And the satellite drag, which is very exciting and personally work a lot with on this particular topics, trying to understand what their need for a satellite drag, and with more and more simulation, more and more constellations launching right now. So again, this is the whole atmosphere model, and this animation shows the storm in April. This is the biggest storm this year, it goes to KP8. We haven't seen KP9 yet, we're pretty excited. Every day I get up first things, look at KP value, see if anything happened, and trying to see what's going on. So this is a double pick KP8 event. You can see our model capturing very good neutral density response. And you can also see those vector wind. So satellite industry coming to me, I also want wind. You realize that those winds are more than 1 kilometer per second. So given the fact that they are flying about 8 kilometers per second in a LEO orbit, it can impact to up to 20 to 30% in their system based on the drag estimations. So I think there are a lot of interesting things that as a scientist haven't learned before, but with a lot of engagement with customer, we started to learn a lot. So what happened? It all started from SpaceX lost their satellite in February last year. So we got a call, and we didn't know what's going on with SpaceX because we know they lost their satellite. They put press release out and said there's a storm. I was like, what storm? What are you talking about? It's KP4. It's KP3. It's G1. There's nothing happened in the past 2 days. And then we started to engage them in trying to understand what happened to their operation mode. How does their satellite looks like? Why are they losing their satellite? So we did a paper study last year, published last year on Starlink event, and we actually utilizing a lot of their data to do that study. And they all give us all the data for research to understand, because again, they understand we can understand better with their data if they give us all the information. So we did a thorough study on what happened to that event and why, and then they're very agile, right? So after they lost it, next week they're launching. They goes to 200 kilometers. They're like, okay, we can't fly 200 kilometers, we'll fly 300 kilometers. So we have interact with them, and they actually even pull off, actually postpone their launch earlier this year because of space weather but they hold on for 6 hours. They launch into KP6. They're like, we can't wait. We have to keep going, and they can take the risk. So we also keep on working with them, and now we have a year worth of Starlink data, means 4,000 satellites in a minute cadence data, to trying to use that information to back derive the density. And we're trying to understand, working with them, trying to understand how to use those information to better specify our model. And then this is two particular activity that I'm highly involved in, is trying to using Cosmic 2 mission to back derive the neutral density environments, given the understanding of the spacecraft orientations, and all the necessary parameters. So we are working very hard trying to come up with the operational data set to support this mission in the future. We're also working SpaceX closely on trying to understand how to use their satellites. And that rely on, they give me everything they have: tank information, propulsion information, maneuver planning, satellite spacecraft size, spacecraft math, spacecraft design, everything. So they're very helpful so far, and I am really hoping 2 years down the road, after this project's over, we are going to full operation in real time with SpaceX data. So I'm trying to tell you that we work with SpaceX, and it's not just SpaceX. Now Kuiper project in Amazon is coming. We work closely with the top tier maneuver services company as well, trying to understand their needs and trying to understand where we can do better job in working with them. So we just had this is the last slide. So we just had a test bed experiment last week in Boulder. So what we did is we called everybody in. So we got all the companies in, and they told us what they want. So for wider variety of group here, what they want is longer term space weather forecast, means solar cycle forecast. They want to know things 7 days in advance. So how do we get there, right? We want 7 days KB forecast, 7 days F10 forecast, because now what happened is we don't know the arrival time of storm. Once that hit L1, we get 30 minutes. You imagine all of them will be dancing there in 30 minutes? Nobody can move their spacecraft. Maybe SpaceX can. But the rest of companies cannot move their spacecraft within 30 minutes. So they can't do anything. So whatever information we are giving them is not actionable. And they're worried, then everybody's moving around, then collision risk is getting higher and higher. So I think there is a huge need to improve space weather forecasts, not just modeling part that I am taking care of. I started to realize that, yes, we can do whatever we want in a model. If I have perfect model in the world, I still can pin down what's going to happen tomorrow. So I think that's where the other community really need everybody in this community to work together to really get that information in to help that industry. And that's all what I have, and I am looking forward to see those questions.
Thank you very much. Hand for our speaker. And we have a whole series of people who are interested in questions, and we have 7 minutes to do it in. So
I'll try to make mine quick. Okay, so you said that it's better to have a standard than no standard. So currently there's basically no standards on modeling software and the outputs from them. What standards would you recommend as we begin to try to navigate that?
What exactly you're asking? What kind of standard?
What standards would you recommend? Maybe make it easier for that research to
right. So when we start to engage that community, I realized one thing. So this whole system of neutral density business used to really rely on DoD system with the tracking data from the classified object. So they build HACCP model to do that density problem. And nobody gets that. So SpaceX is doing something themselves, and Project Kuiper doing something, and everybody has 300 satellites. Everybody I talk to, now people are very modest. They'll come and say, I only have 70 satellites. But now it's like everybody will have 300 satellites, right? So how do you make sure there's a standard in the community? So we're really working with Office Space Commerce hard on this problem. We're spinning off a new project, trying to build a commercial, rely on commercial data, a new density model, so that commercial sectors can start using that kind of standard. Because you're talking about, you are seeing that something coming. I am not seeing something coming. Then I'm going to move to somewhere else. So I think that is a huge problem, and that they know that's a problem, but they can't set it up. So government need to step in, trying to kind of build that up as a government backbone service. And then they can interpret it, they can use their data to do a better job if they can. I hope that kind of answer your question, but no.
So what standards would you want to see on how models run, perhaps, and formats of the data they output?
I mean, there are a wide variety of that question is a lot, right? So we have F10, we have KP, and it goes into the model. So there's no standard right now.
So why don't we hold that further discussion
Yeah, we'll do
and
that.
move on
Yeah.
to the next
Sure.
question.
Another excellent talk, and I wish I was at your testbed panel last week. So when it comes to forecasting, and we use that word so ubiquitously that it's a little bit upsetting. So far, all we do is nowcasting from 30 minutes, as you said, from L1 observations. Forecasting requires understanding the sun.
That's right.
And my question is, when we create models of total electron content, I mean, it's varying because of what the sun is doing, the EUV measurements, right? So what kind of, and I heard the word F10.7. We know if 10.7 really doesn't drive the ionosphere. It's a proxy, but we have good data, right? Extreme ultraviolet, and you can back generate it, all sorts of things, but that's not used by the community to generate TC. So I'd just like to hear from your side as you're doing, real operational forecast. What kind of steps are you taking, and how could the scientific community work together more closely to make this better?
So we do have intention to use the UV data that is coming real time from GOES. I mean, that's something my team taking very serious. We're going to try to use that in the coming.
From SDO since 2010.
Right. And then when I talked to the customer last week, say, oh, but how do we use that? I said, I don't know. So I have a lot of I don't know questions because they are used to use F10. Models are tuned toward F10. So today I can totally imagine when I started using UV in my model, it's going to come high. Everything going to come high. We have to reskill things again. So it's not a trivial step, even though it's easier to say we can get that data into the model. But I think kind of really think, and I don't know how do I do future forecast, right? So if I run model with EUV right now, how about tomorrow? I don't have EUV forecast. So I think it's a really tough question, and we all need to work together on solving that steps. And then, forecast tricky. And then with one spacecraft, two spacecraft in O1, we're not solving that problem anytime soon.
Well, we should talk. These are important working group discussions.
Exactly. So I almost feel like I talk to customer and I can't handle that question myself because I can't ultimately deal with forecast question by ourselves, even by our center.
Thank you for that presentation. One of the topics here is open science, and Jen showed how much you can do with impact data back from the users.
Right.
And it sounds like you work a lot with users. You're getting information from SpaceX. So what are you doing to make that available to the rest of the community?
So that's just really something we have to think about in the future. I mean, they have intention to release their data, but they also want to make sure it's really useful. So I have feel like I'm sitting on a gold mine, and they show me all kind of things. I was like, give me the GPS receiver data, give me the magnetometer data. We're trying to do something. But I think we'll have to see how that goes. And since SpaceX is showing up that standard, I have a lot of company coming behind me. I also want to give you the data. You want planet data? You want Kuiper data? I say, yeah, but let's do one step at a time. We have not figured out how to do that. And they are very cautious because we are getting. So for our paper, we release a subset of data, which doesn't have all the information that they're giving me, but they're comfortable with that. So maybe we can start with the simple ephemeris. And they're pushing that in their community to everybody has to give ephemeris data so that they can avoid the collision in the future. So I think their community had that drive. And it's how we use that information is something we have to work harder on that. But yeah, there's an intention they should be giving all the data openly so that we can all help them to solve the problem.
Hi, great talk. So I'm going to sort of counter Lika's point, which was, what about the solar side? What about the quiet time? You built a whole atmosphere model now. What's coming up from below? Gravity waves, that kind of stuff. How interested are your customers in what's going on in the quiet time?
Right.
Because that is a source of predictability. If you have a stratospheric warming, you have other things, you could get a week's prediction skill from that, right?
Right. I like what we're talking about beginning We used to talk about big storm. Now we're looking at smaller storm can cause disturbances, right? And I have started to give a lot of advice to students working on MLT, working on gravity waves. Everything you learn is important. You know what happened? Now people coming to me for insertion, like insertion orbit predictions, re-entry predictions, VLEO missions. Everybody want to fly 200 kilometers. Everybody want to fly stable at 300 kilometers. But our model cannot do well because we don't know how the MLT look like. We never even focus enough on that. So I think those are becoming critical. And we can see that. You are seeing like 10,000 satellite up there at 500 kilometer. I think we're thinking about 100,000 in 5 years down the road. So how do you do a quiet time, solar minimum conditions, trying to get that accuracy correct is become very critical.
So a quick question of clarification. Early on, you said there's all this free data that you're using.
Right.
Who paid for that data? Who built those sensors?
We're trying to utilize a lot of geodetic ground-based GPS receivers, right? So those are really for people doing positioning.
Okay, so it's companies that put it out, or it's an SF
Yeah,
that funded it?
we had a lot of government ground-based receivers, and they're also private. Not as many private, but there are a lot of need for geodetic receivers right there.
Okay, so it's free to you, but
Right.
it costs money to put those sensors out and to
Exactly.
operate
And then
those
we do,
sensors.
I think NOAA need to find a way, since NOAA just doesn't want to take care of ground-based receivers, we are really trying to spin off something, National Weather Service, to take care of our ground-based receiver, just like weather station everywhere in US, right? We need to have that infrastructure set up to do space weather as well.
Okay, so I've made a command decision to give us 5 more minutes for questions and answers because there's enough discussion going on.
Sure.
So I think that's 3 more questions.
Thank you for your talk. I just encountered one problem regarding data. You have explained that event of April 2020, 21-22 this year. This was an extreme storm of the 25th solar cycle. What we face problem, we use your data, that ACE and Discover spacecraft real-time data, and when we communicate with the referee and the journal, they told that you cannot use this data for your performing that science work. You're doing absolutely very, I appreciate your effort regarding forecasting and all, but what we have receiving from this referee and journal is about, they required L2 type of corrections in the data, and your real-time data is like moment analysis that on the spacecraft only. And if we wait for the L2 data, which is available on Omni, we have to wait for the 2 months. So it's my humble request from my side that to publish that data as possible as that L2 in a real-time aspect.
Okay, I actually agree with you. Last week we just beaten by the satellite industry. It's like, why don't you give us that? Why don't you give us that? Why don't you give us coronagraph? We'll figure out everything by ourselves. So I think there's urgency just to release as many data as possible to not just researchers but the industry as well. But yeah, I think giving out, I have a hard time finding out our data after 3 days. Like, where is that value? So I think there are a lot of infrastructure need to be built to stimulate that open source data.
I think I have the next question over here.
Oh,
I
yeah.
see. Yeah. So I wanted to go back to the first question that was asked about data formats, open data formats. And, at NSF, we've been talking a lot about the ground-based data and how there's a lot of trouble with the community being able to use data from different places and how can we work together to do that. And, I think Ken Tabisca in particular had really been pushing for standards, and the UN has a whole, area that works on that. So do you think it's, the time to really push, from NOAA side to have some kind of standardization so that there can be progress and be able to actually answer a lot of these questions about what is space weather, what is not in these data sets?
I would say there's a big push within NOAA and DoD, Space Force with UDL activity. We all want to use JSON file, but JSON is not something human readable. The other end of my customer is sitting there, I just want a CSV file. I don't want a text file. I want an ASCII file because that's what I've been using. It's easy to read, easy to interact. And I have somebody coming to me and say, what is NetCDF file? Like companies sit on it for a month and figure out, what is that file format? We've never seen that. So I certainly think there's a big need, but I personally have no idea how to get there because I have that issue all the time, right? I look at JSON file myself, then I can like, okay, then we also produce NetCDF format. We think that's great because we're used to it as a scientist. But how do we, I think it's gonna be very hard for that industry to take on what we have. I actually think the best way is just every format we create, we come with a reader with it, kind of translate into some language so that people can, we have this issue with the ICAO activity also. Every country is producing files different format. And then they want us to all convert into a format. That process was painful. So I actually don't know how realistic we can push that directions in terms of data format. And not to mention, you're talking about hundreds of customers. They want to do whatever they want to do. They're not constrained by what we're doing. But yeah, we can do a better job internally and in the research community to give a better format that we all agree on and then force them to use that. But even that, in our center, we have so many different formats that we try to push things, but it's not trivial. But GeoJSON seems to be reasonable directions that DoD and Space Force and us are moving forward.
I have kind of a more philosophical question. So as satellites get smaller, like CubeSats become more popular, and customers launch larger constellations, they can maybe afford to lose more to these extreme space weather events. So how does that change what kind of models and what their needs, what kind of models you're providing the customers and what their needs are to you? Like, how do you see that evolving over the next 10, 20 years?
So when your satellite is smaller, your drag impact is bigger. And we've seen that. But I also start to see things are different now, right? In the past 10 years, we see satellite going smaller and smaller CubeSat. Now we're seeing they're building bigger and bigger again because our launch capability has changed. Looking at Starship launching in the coming years, SpaceX targeting bigger spacecraft with 700 kg, 2,000 kg. They don't want to do 200 kg satellite anymore. So I actually don't know how to answer your question, but I think we trying to see how that our information gonna support that. I guess I didn't get your questions. I mean, how do you use that? It really depends on how that industry evolve and how we can meet their need. Because a lot of times, I mean, probably understand the first generation Starlink spacecraft. When I see that, I say, your spacecraft was designed horribly. And they say, you're right. So I think they get smarter also trying to understanding what we are trying to do. But yeah, just with that constellation number going up, we certainly want to take advantage of that data set.
So how about another round of applause for our speaker? I think that was a really good discussion. So we're running about 10 minutes behind. The next speaker is, and I'm going to apologize, Omana Ilodor. Great.
My name is Omana Ilodor. I'm here to present my talk titled The Response of the African American Equatorial Ionization Anomaly to the 2014 Sudden Stratospheric Warming Events. General background of the study. Previous studies have shown that variability in the ionosphere during sudden stratospheric warming is connected to the coupling of both the lower and the upper atmosphere. Understanding this connection between the lower and atmosphere is a relatively new event because the first discovery was occurred in 2008. SSW events are meteorological events that are characterized by the breakdown of the stratospheric polar vortex arising from dynamic forcing originating from the lower atmosphere. But the Thayer et al. In 2018 presented a global picture showing the variability of how sudden stratospheric warming affects all the regions of the ionosphere, from the lower atmosphere to the upper atmosphere, and also affects the general atmospheric conditions and climate generally. SSW events are generally classified into two: major and minor warmings. Major warmings are actually due to the reversal of the zonal wind flow, while minor warmings, we do not have the reversal of the zonal wind flows. So I got my data in the course of this analysis from NOAA, where I got my stratospheric and zonal wind data. For the observation of the ionosphere, I used tech data from a chain of different networks, shown above. Then we also use the magnetometer data to actually determine the equatorial electric jet current and a proxy for it by determining the vertical drift. Also, the 2014 SSW event was unique because it occurred during the maximum solar phase, so we had some geomagnetic storms that impeached with the event. And the occurrence of this geomagnetic storm, in order to investigate it, I had to use data source of F10.7 and the PPF electric field from series model in Colorado. So the general methodology for carrying out this research still remains the normal way that was adopted by Concharenko et al. In 2008, where we first of all have to determine the quiet condition of the ionosphere. And the quiet condition of the ionosphere is the period in which we are looking at the ionosphere before the perturbation arising from the SSW event. So these days are generally classified as quiet days in which we use a KP index of less than or equal to 3. After determining the quiet days, in the days in which we have the surge in the stratospheric temperature, we actually separate the anomalies by subtracting these quiet days from the actual tech values during the SSW event to see the anomalies actually arising from the SSW event. Furthermore, to actually observe the overlaps of the geomagnetic storm with the SSW event and actually to isolate the geomagnetic component, we also had to look for days in which we had quiet SSW events that occurred and subtracted it from days in which we had the overlap of the direct SSW event with the geomagnetic storm, so that we could be able to isolate the geomagnetic component only. So, in order to explore the variability that is arising during these events, we also used the ROT and the ROTI formula to determine the irregularities. A cutoff of 30 degrees was used to reduce multipath effect. Then, in order to eliminate spikes arising from the ROTI, we used the ROTI average, which actually eliminates noise spikes from the ROTI. For the equatorial electric jet, we adopted the technique of Rabi et al. And you estimate the vertical drift, we use Anderson 2004 model, which was a neural-based model to determine the vertical drift. Then we also compared our electric jet current with that of SQUAM data to actually see whether there was a consistency with our ground-based result with that of the satellite result. This is a map of the GPS station which shows all the results we use. The chain of satellites, as you can clearly see the results from the map. We use the geomagnetic coordinates in which we looked at the span of plus or minus 40 degrees in the northern and southern hemisphere to actually characterize the low latitude to the equatorial region. General results of the study. The figure below just shows an overlap of the SSW criteria we use, where we have the stratospheric temperature shown in green. We have the reversal of the zonal wind in purple. The blue color actually shows the historic mean temperature, and the intercept of the historic mean temperature with that of the stratospheric temperature gives us an idea of where the SSW event terminated. So in order to also look at the conditions of the geomagnetic storm within that period, we use a KP index. Generally from our results, we had KP index that was generally below 5, except on 19th where we had KP index that was above. So for the properties of the SSW event, I summarized it. The SSW events, we had 3 minor and 1 major warming during the period of the study. And the days in which these events occurred, they occurred between the 2nd and the 12th, the 17th and the 25th of February, the 27th and the 10th of March, and the 14th to the 20th of April for the major warming. The properties of the SSW are shown in terms of their peak temperature and in terms of the days in which they occurred. Also, for the major warming, we had a reversal of the wind component at approximately 70 meters per second. So for the geomagnetic storms that occurred within this period, we had for the month of February, we had 4 geomagnetic storms. We had a 2-peak storm between the 19th and 20th, and then we had 2 moderate storms that occurred on the 23rd and the 27th, while we had also a moderate storm that occurred in April. So general results. Figure 5 here shows just for the month of January, the quiet condition prior to the onset of the SSW event. We observe from this figure that the tech values were generally low in comparison to the days of February, where we had increase in tech values, which is shown by the color scale increase in the tech values. So from our results, we can clearly see that when considering the tech values, we had for the first minor warming, no significant increase in tech in the African sector, while in the American sector for the first warming, we had higher tech concentration in the northern hemisphere compared to the southern hemisphere. For the second warming, we observed that on the 20th, there was suppression in tech values in both the African sector. In the African sector, why we had announcements on the 20th and suppression on the 19th. This value just simply shows the response of these sectors to the geomagnetic storms that occurred within those periods. Then we also observed that within the period of March, when the actual major warming occurred, we observed that there was a particular feature of the result shows a suppression in the tech values from the 25th to the 26th in both sectors, showing an equatorial response of the African sector to the SSW event, which was the day of the reversal of the zonal wind. So generally, in order to compare the response of the geomagnetic storm with that of SSW, we decided to compare the quiet days prior to the SSW event with that of the SSW to actually see the actual EIA crest locations for this event. Then we also calculated the quiet days for the respective months and compared them with the days of the storm itself to actually see the forcing effect associated with the geomagnetic storms, as shown in the table above. So now to the SSW event itself, we observed that after using the procedure of Concharenko et al., we observed that for the period of the SSW event, that we had semi-diurnal variations for certain days, and we also had higher tech concentrations also for certain days. The ellipse indicates the periods where we had diurnal variation associated with SSW events in both the African and in the African sector, whereas in the American sector we had nothing like that. So generally in our study, we also separated the removal of the geomagnetic storms, and this was the result we obtained for the days that we had the direct overlap between the SSW event and the geomagnetic storm. For the tech, our result shows that there was a weakening of tech in the American sector due to the SSW event, while there was no effect arising from the SSW event in the African sector. For the PPAF and the EEJ signatures, we observed that these values are generally higher in the American sector compared to the African sector. So the general conclusion of the study showed that the geomagnetic storm and the SSW event actually had effect on the ionosphere, that the SSW event as a reversal of zonal wind resulted in the suppression of the tech in both sectors, and that tech was generally higher in the American sector compared to the African sector, and generally SSW forcing in the American sector weakened the irregularities. Thank you.
Thank you. Thank you. We're going to hold our questions for the end of these two speakers. Okay. So the next speaker is Aidan Thayer. If you'd come up and go ahead and make your presentation.
Hi, I'm Aidan Thayer, they, them. Here to do an observational study of Southern Hemisphere polar moving radar aurora forms using 2021 SuperDARN data.
Sorry.
Do I just click the green button?
The green button.
Okay. So the first question you might ask is, why exactly does this work matter? And the simple answer is satellites. So background EUV creates plasma, as we all know. plasma is created all the time in the upper atmosphere, but during periods of high solar activity or a flare, more plasma is generated. This temperature profile change causes introduced energy. You can assume the upper atmosphere is hydrostatic. This temperature profile change causes expansion. Higher density air reaches low Earth orbiting altitude. Low Earth orbiting altitude always faces some drag, but drag increases as density increases. Satellites must therefore regain speed. And if the satellites don't have any station fuel, the satellite's lifetime in orbit is limited. Here on the lower right is the equation for satellite drag coefficient. And as you can see, there's the ballistic drag coefficient, which is constant, cross-sectional area, which is constant, satellite mass, which assuming you have no station fuel, which would be constant, atmospheric density, which is the only changing factor. An example of this, of course, happening is with Starlink, as we all know, as was discussed in a previous talk. So for this talk, I'll be talking about a period of the upper atmosphere, or a portion of the upper atmosphere between 100 and 300 kilometers. On the left graph here, you've got temperature on the x-axis and altitude on the y-axis. So you can see it's looking at stuff that's about 1200 Kelvin in the thermosphere, and then plasma density, you're looking at the E and F regions where photoionization is very important. So the day-night side reconnection actually matters quite a bit. And on the right side, you've got plasma density on the x-axis and altitude on the y-axis. And for this, you can see, as I mentioned, the importance of the day-night side, because during the day, you've got the F region, and during the night, you've got the E region. Let's skip this slide. So to do these measurements, I use what's called SuperDARN, the Super Dual Auroral Radar Network. It measures plasma convection in the EF regions of the ionosphere. It uses Doppler shift to determine plasma velocity, and it combines radars to determine direction. I use two different radars, the McMurdo station and South Pole station. In the lower right here, they are the two blue triangles that are not particularly oversecting. So this one here and this one here. And then as an example of what it looks like when the bow shock intersects with the magnetic field, see the graphic with the little cartoon in the lower left. And then a background into some of the parameters. Everybody's familiar with what BX, BY, BZ is, the solar wind's magnetic field components. But if you're not, look at the lower left. Here's BX, BY, BZ. But for some people who are not familiar, there's the auroral indices AU, AL, AE, and AO. They're magnetometer measurements of the northern hemisphere, depicted here in the lower right. They're taken from quiet day measurements of the lowest 5 days over a period of a month. And then you subtract off the lowest 5 days. And then you can then determine AU is auroral upper, which is the top 8 measurements, and auroral lower is the lower 8 measurements. AE is the mean, AO is the difference, and then SIM-H is the geomagnetic disturbances of mid-latitudes, which is very similar to AU and AL, but is taken at mid-latitude magnetometer measurements instead of northern hemisphere magnetometer measurements instead. So those are the indices that I'm working with for this project. So now talking about the phenomenology that I was working with for this project, poleward moving auroral forms. Here's what it looks like for localized reconnection. Plasma convection coming in, the open flows boundary. Here's what the radar field of views look like. and you can see what looks like a forward-moving auroral form coming into the radar, South Pole Station or McMurdo Station, and you can see the plasma coming in. The plasma convection, this is actually drawn not quite to scale, but it's a cartoon, but it's drawn so that the plasma convection is actually accurate in direction, so that you can actually see that the forward-moving auroral form will move across the radar and South Pole Station from right to left, and then through to McMurdo, across down. And I'll be showing that in some videos later. So then talking about forward-moving auroral forms, they're normally considered a visual phenomenon that people look at with all-sky cameras. Here's a picture from Sandholt and Ferrugia. They normally last about 5 minutes. They are considered to be strong responses of plasma convection. There's pre-noon and post-noon PMAFs. People know them as being strong indicators of BZ, or being driven by BZ, excuse me. But like I said, they sort of extend over about 5 minutes. So they, as you can see in these panels here, this yellow line is magnetic noon, and they appear, sort of develop slowly over about 5 minutes, and then disappear. So then I was looking at forward-moving radar auroral forms, which are the radar signature of PMAFs. So the key features of the radar signatures are that they're localized dense plasma, fast-moving convection, repeated waves with 2 10-minute gaps. They occur near magnetic noon, and they're linked closely to traditional PMAFs. And so what I did personally is I categorized 60 of these events throughout 2021. I attempted automatic signature detection with Fourier analysis technique. This didn't work out, but that was the goal, to be able to link them with other years. I confirmed what we call McMurdo streaks for 21 of these events, which is basically 21 of these events. I confirmed that they also existed for a different radar. I pulled IMF and auroral indices from Supermag and Omni database for all 60 of these events. I ran basic statistics on these indices. And then I used the model to run convection mapping software for 21 of these events. So here's what a PMRAF looks like on an RTI, which is a range time intensity. So the x-axis here is time, the y-axis is range, and then the color is intensity and power spectrum. So basically how much plasma is being reflected here. And the black box top panel is South Pole Station, bottom panel is McMurdo. And the sloped here in the black box is what PMRAF looks like. And you can see pretty clearly the movement of a PMRAF moving towards moving away from the station, the radar. It's also very clearly dense plasma. And it's, in this case, it's several PMRAFs moving back to back to back. So it's not actually 2 to 10 minutes, it's about 45 minutes. But the McMurdo streak, which follows after it, which you can see below, is, I wish I had a laser pointer, is lower. And so then to show this on a video, apparently I don't have a video. Cool. I do have a video. Fancy. Can you control click this video? Okay. Sure. we'll skip past the second one. So with the conclusions, I checked IMF auroral indices and symmetrical correlation with the onset of permafrost, and I found that BY and AL showed weak correlation with the onset of permafrost. Other indices showed no correlation. I checked for non-zero mean standard deviation, did a Pearson R test. When I say a weak correlation, basically I found a non-zero mean and a non-zero standard deviation, but it did not send it to a Pearson R test particularly. This is interesting because you'd expect to see a BZ correlation based on prior research, but it was not found. So that was particularly interesting. I also did not look at seasonality, which is another particularly important thing. And then you can see the histograms of AL and BY here in the lower left and lower right. And none of the other indices showed any particular trends. So that was my conclusions. Thank you so much.
Omina, if you would go on up, we're going to go ahead. We're going to have some questions and answers. We have about 10 minutes for Q&A. Anybody have questions?
Regarding the your presentation on the effect of the stratospheric warmings on TEC, there are now models that do this, that simulate the whole atmosphere. Have you thought about accessing those to see how they would compare to the observations?
Yes, there are a lot of models available. We have the whole atmospheric model. We have time GCM models, but most of these models have different regions in which we are looking at, and also the forcing of these models also generate different results.
Okay, any other questions?
Aidan, this is a question for you, and I don't have a lot of knowledge in your subject area, but are you planning on continuing this work with any of the IceCat 3D systems that are coming online soon?
No, I'm moving institutions, and so as a result, I'm moving topic areas as well.
Okay, any other questions?
It's not a question, but comments. Like, you know, when we do space weather research, you gotta really figure out what you're talking about, right? So I know it's a lot to learn. So flare doesn't cause thermosphere density increase. Flare causes ionosphere density increase in different altitude. And then CME coming hit the Earth increase the KP and solar wind parameters, and that's why the whole thing increased on the Earth. Right, so just be careful when you talk about satellite drag. We're actually talking about neutral atmosphere, neutral density. That is 6 order of magnitude bigger than ionosphere we're talking about. But they're all connected, right? So how does the electric field that you are observing impacting ionosphere, impacting thermosphere? They'll come with different time scales. So just when you study, just be a little bit careful and look into some of these questions that, just keep curiosity and make sure that you understand the physics. So something just to think about next time. Thanks.
Okay, I think that's it. And so now for the good news, we're up for a break. Oh, I'm sorry, one last round of applause for our speakers. So the break is 25 minutes.
So right now, using a single way, but we're using
Check, check. If everyone could please take their seats, we have Craig DeForest up next. If everyone could please take their seats, please.
Hi. This thing's on, right? Yeah, okay, good. All right, so as we finish up our break, I will jump into a topic that I've sort of been working on for 20 years, and we've been working on as the Punch mission for 7 years, 8 years, eight. So may go a little fast in places. Imaging the corona and solar wind with open science tools and with Punch. First of all, Merry Christmas. Those of you who are old enough to remember when computers counted in base 8 will remember that octal 31 is decimal 25. So, all right, for the rest of the talk, here's the outline. We'll talk a little bit about imaging science, the corona and the solar wind. That's basically what we're doing with Punch and why we're doing it. I'll talk about the challenge, or some of the challenges, of coronal and solar wind imaging and why we bother. We'll dive a little bit into esoterica there, but really just dip our toes over the side of the boat into the waves going by. What does open science mean? I'll talk a little bit about that in the context of Punch, which is an operating mission. Well, we're not operating yet, we're in development. But how it applies to folks who are running a particular project. And then finally, how to get involved with Punch. So, imaging science, the corona and the solar wind. Let's see, this is what Punch does in a nutshell. On the left, you see a LASCO time-lapse movie of the outer corona with CMEs coming out. These are, of course, sweeping out through the solar system. And in the background, you can see these linear features are carrying solar wind, which fills the entire solar system. And of course, the stars in the background. The sun is to scale there. This sort of represents how we study the sun with remote sensing, radio, visible light, EUV. We look at electromagnetic radiation coming from the sun, and that's largely how we understand the star. Meanwhile, we study the heliosphere and the solar wind itself and its impacts on the Earth by sampling that in place, as represented on the right by a series of traces showing velocity. Let's see, is this actually, where's the laser? Oh, right here. Aha, okay, so on the left-hand screen, you can see velocity, density, temperature, and magnetic field, and there are several other parameters we can get at a single point in space by launching a probe out to get the wind sweep over it. Well, we're at a really interesting time in these fields. We have Parker's Solar Probe now, which is carrying these kinds of in situ measurements directly into the corona. And that is terrific because you absolutely have to have that ground truth to understand what the plasma is doing. But there's a problem with this kind of measurement, which is understanding the global structure of the environment. I like to say, if you want to study human anatomy, the wrong tool is an electron microscope, right? The electron microscope will tell you everything about what's going on in a cell, but it won't tell you about how sinews connect to bones and that kind of thing. So we're trying to bring out, with Punch, imaging science into the solar wind to get the large scale and cross scale information that we can't get directly from in situ measurements. These are very complementary ways of seeing the system. And by bringing both of these to bear, we will be in really a new era of unified science of heliophysics. All right, so I'll be very fast here. Punch is a mission with 4 spacecraft that will be imaging the entire inner solar system out to 45 degrees away from the sun. So we are not a telescope. We'll be imaging plasma as it sweeps out from the sun and over us. We're taking polarized visible light images. So in some sense, it's like a super coronagraph. We'll be in sun-synchronous polar orbit, looking at the sun all the time. Right now, we are in phase C, assembly and test. We're getting ready for final integration. Our next milestone is pre-environmental review in 24. We're about to do a system integration informal review later in the month, this month. We're planning to launch in April of 25, so we're in deep prep now. All right, this is some of our science. I could talk about this for a whole hour, but I'm not going to. Loosely, we have things about the solar wind. The global and evolving solar wind flow never really been measured routinely near the sun. The Alphane zone, sort of the last frontier of the inner heliosphere, the place where the solar wind exceeds its own wave speed as it leaves the sun, and becomes causally disconnected from the sun. So we plan to image that. Solar wind microstructures and turbulence. These are sort of ambient solar wind studies. And then up above, we have the more bright and shiny stuff, coronal mass ejections, shock dynamics in the heliosphere, and co-rotating interaction regions, the unsung thunderstorms of space weather. They're responsible for more geomagnetic storms than CMEs, although the strongest ones come from CMEs. So that's our science. Here's just a taste of what we're looking for in the outer corona. This is a very deep field coronagraph movie that we made with the stereo Core 2 coronagraph. We ran extra long exposures and then post-processed the data to remove noise. Now there's a coupling between different aspects of data, and this is true for any data set. In images, one of the surprising couplings is between noise level and resolution. So by beating down the noise level, we were able to bring small-scale structures out of the noise floor and show that the outer corona is extremely structured. It is very highly structured, all the way down to the optical limit of this instrument, which was a surprise to me at the time, but should be a surprise to no one if you've ever looked at just how wobbly those in situ plots are. The structuring is not just spatial, it is temporal too. If we remove the average brightness of the corona, you can see that there's stuff leaving the sun all the time in all angles. And this was so surprising that we called it a riotous torrent, that the data are in fact consistent with the picture of the solar wind as only a collection of ejecta, not a smooth flow at all. They don't tell you that it's only ejecta, but they're consistent with that view, which again was a surprise to me. We've all learned about, many of us have learned about the Parker solar wind solution for smooth flow leaving the sun, and that's sort of the paradigm that we all pick up in graduate school. But in fact, that's not all that's going on by a long shot. So we'll be using these small features to trace the wind flow speed. And we'll do that about every 6 hours compared to Ulysses, which did it once every 6 years. So we expect to find a lot of interesting things. Many of you have seen this movie before. This is a polar coordinate movie that connects the sun on the right in the EUV out through all of the various stereo fields of view from the 5 instruments on board stereo, out through the coronagraph field of view and into what is now called the heliospheric imager field of view. And we traced particular CME, this one, all the way across the solar system, as it swept over the WIND spacecraft over there in that circle, you can see the solar wind gauge pegs really closing the loop and showing that, in fact, yes, material from the sun really does sweep out across the solar system and sweep over the Earth. Pretty excited about that. There are some really important gaps in here, important because interesting transitions happen between these fields of view, and it's not clear whether it's the instrument or whether it's the plasma itself. So unifying those fields of view is important. With Punch, we are covering from the outer corona out through all of what in stereo is the high one field of view, and we're eliminating these seams here so that we'll have a continuous view all the way out. Over on the right, you can see this polar view on the left sort of hides the fact that you can't really see over the poles of the sun with stereo. And so with Punch, we're looking all the way around so that we can see how the solar wind leaves the star even over its poles. These are our observatories. On the left, we have a small sat with a coronagraph on it called the Narrow Field Imager, or NIFI. On the right, we have 3 equivalent spacecraft. They're actually interchangeable, with a different instrument on it called the Wide Field Imager, or WIFI. These are in fact the same instrument, just one's in linear geometry with a baffle here to block out the sunlight and provide an artificial horizon for a camera back here. And over here, it's in circular geometry. We have a circular occulter at the center that blocks out the sun so that the instrument can look close to the sun and see the entire corona. We also have a student energetic activity monitor. That's an X-ray spectrometer that's flying on the NIFI spacecraft. It was built by Colorado Space Grant Consortium. I'm pretty happy about it. And they were the first instrument to deliver to the Punch integration flow. So I'm pretty pleased about that. NFI has been delivered recently. This is a picture of it at the Naval Research Laboratory just before it left, just a few days ago on the 19th. And is now in San Antonio in our clean room, ready to integrate to the spacecraft. Over here on the right, this is a picture of it working at the test facility at the Naval Research Laboratory. This is sunlight shining on the front aperture. This is the occulter that I mentioned. And the aperture is jagged to prevent diffraction of sunlight off the outer edge. So neat stuff. This is the Wide Field Imager. We have one that just went through its pre-ship review and is about to be shipped to our clean room, 2 more that are still in development. This is just before it got, it's stray light testing. Let's go back. Stray light testing, again, at the Naval Research Laboratory in their vacuum stray light facility. This thing occults light so well that the Rayleigh scattering of air in the room is much more intense by about a factor of 1,000 than the instrument itself. So you have to test it in vacuum. This is a picture through the instrument taken of the inside of the vacuum chamber and demonstrating that there is no perceptible bright line here. So we're attenuating stray light by a factor of 10 to the minus 16. So we can look at the very darkest things in the solar system in the eternal noontime of space. So I'm pretty pleased about that. This is how the instrument works. On the left, you have a star field. The instruments are all looking out from the Earth onto the star field as they orbit the Earth. The pattern that they make on the sky with their fields of view rotates. And so each one of these is the field of view of one of the cameras that we're going to launch. They spread out around the Earth, and they form this trefoil in the sky, which rotates and paints the entire inner solar system once every 30 minutes or so. Inside of about 10 degrees away from the sun, we get an image, a polarized image every 4 minutes. Pretty rapid. The problem, of course, is we have to merge these fields of view on the ground. So we'll do that. Just to give you a sense of scale of our field of view, that trefoil is 90 degrees across, so it would go from the horizon to the zenith. This is it painted onto an eclipse picture that was taken not by Drunkmuller. This one was taken, I think there's a Drunkmuller overlay here, but the image was taken by our own Nikki Weil at the 2017 eclipse. And these are some houses and things just for general scale of just how large this field of view is. Punch is not a telescope, right? We're viewing things that are actually sweeping over us as they do so. All right, so that's sort of a brief taste of our science and what we're doing and the instruments we're using to do it. I want to talk a little bit about the techniques and challenges that are required. We do a lot of post-processing of our data in order to get to the features we need to see. And this ties directly into something that's near and dear to my heart, which is open source software and science. There are a lot of steps to our pipeline. Up here, we get data straight off of a camera. I'm not going to walk you through all the steps. We do a lot of things to calibrate it. After the data are calibrated, we sort out the polarization signal that comes from each camera, and there's some transformations that have to happen there. And then we merge the data into mosaics. Then we remove the backgrounds. And there are a lot of backgrounds. So these are easy to put on a big plot like this, hard to walk through, which I'm not going to do, but even harder to execute. Down here, these are the data products you get, which are coronal images that look very much like that Lascaux movie, only with 30 times less noise and twice the resolution. Pretty pleased about that. So you'll be able to work with those directly. They arrive in standard formats. This is just an example of one of the challenges. We have these trefoils coming down. Our Science Operations Center is already working on how to merge them into mosaics. It's easy to say we're going to merge data into mosaics. It's really hard to align star fields to within 1/30th of a pixel and taking into account all of the optical distortions in the instrument. But we have a handle on it. We're going to be ready. One of the things we had to do in order to make this happen is understand point spread functions. If you've ever looked through a telescope or a camera, you probably understand that a star doesn't look like a point of light on a detector. It's smeared out in a uniform way by a telescope. This has been a problem for some time, as described in Dioptrice by Kepler in 1611. So this is driving telescope design. And what we found is a way to post-process all of our images to produce a fake uniform telescope out of all of them. So we can take our, here's some math. I'm going to show you the math. I'm not going to walk through it. We do convolution and deconvolution. It involves the Fourier plane, really neat stuff. This is the outcome. We start with starfield images, and these are composite starfield images assembled from a real starfield taken with the instrument. The engineering model went out to McDonald Observatory in Texas and photographed the stars for a couple of nights. So these are actual trails that are imposed by the instrument in different parts of the field of view on the stars in that general vicinity. This is after we post-process those data. And so we can produce a virtual uniform instrument that allows us to merge the data into a single uniform field of view with known characteristics.
What's the residual problem? It's not perfect. So what's the...
Well, the residual here is partly because our calibration wasn't great for photometry, partly because I've really pumped this to show off the tails so you can really see what's down in the crud. This stuff here is just noise because we couldn't run the camera cold enough. It was in air. It's designed to get cold in vacuum. So there's a lot more noise than there will be in the actual data. But this represents about a factor of 10 to 30 reduction in the strength of that tail. And in the real data, we'll do better than a factor of 100. This is summarizing why this kind of imaging is hard. I love this plot. This is angle from the center of the sun. The sun solar radius is 1/4 of a degree. That's why this ends at 1/4 of a degree. It's a logarithmic scale going out to 45 degrees from the sun. What you're seeing is various brightnesses here: desert sky, mountaintop sky. During an eclipse, things get much fainter, and you can see the K corona, this green line here, close to the sun. As you get farther away, the K corona drops below the zodiacal light, or F corona. That's light from the various bits of dust orbiting the sun in the same general plane as the planets. And then sort of down here, city night sky, full moon, galaxy, stars, Earth's atmosphere glow. All these things are sort of brighter than what we'd like to see even 10 degrees from the sun. That means no matter how good our instrument is, we have to post-process the data to remove these backgrounds. And it's challenging. This is a logarithmic scale. This is a factor of 1,000.
right? So we have a big job. There's the punch field of view, right where it gets hard. I just want to walk you through the steps that we do with stereo to do this, to show you that we can. So this is a star field taken with stereo back in 2008. This is Pisces up here, if you can recognize it. This is Venus and some CCD artifacts because Venus is so bright. This is the Earth and a CCD artifact of it. This is a piece of metal that obscured the Earth from the detector a little earlier in the orbit, but the Earth has since moved out. These, I'll call your attention, this is 0 to 30 counts per second over an exposure. And these are 2-hour exposures. So 0 to 30, remember that number. All right, first thing we do is coronagraph treatment. We subtract the background and you can see the stars. It looks like there's a lot more stars now. That's because we're 0 to 1. So I've gone in by a factor of 30 in the photometry. Next, we resample to fix the stars. We subtract the star field based on its stationarity in this frame of reference. It's stationary, so we subtract it too. And we end up with this. Now look at the scale, 0 to 0.1. Okay, so we're a factor of 300 inside the original data. This is sort of residuals that are left over from the fact that we're orbiting slightly out of the plane of the F corona, so the F corona is moving slightly. And then these streaks are leftover statistical residuals from the star field that we subtracted. We can still get rid of them if we fit a polynomial to each pixel value in the sequence and subtract that. You can start to see this structure sweeping across. If we use a motion filter in Fourier space, we can get this. And we can now reveal the solar wind. This is 0 to 0.03. This is a factor of 1,000 inside the original dynamic range. So that's what we're doing routinely with punch. And it's a challenge, but we can do it. And I threw these slides up just to kind of reassure you that yes, in fact, photometry really works. And then when we average across batches, we get this. And we did a lot of science with this kind of movie using stereo. Punch will only go out to 45 instead of 90 degrees, but will have roughly 10 times the spatial resolution of stereo high. So again, lots to see. One of the things that we expect to do is 3D imaging. That's really exciting. Here's how it works. We have multiple spacecraft, but they're not far enough apart that we can use stereoscopy. So we use the polarization characteristics of the light. What we're seeing when we look at the corona is light from the sun that's been scattered by electrons. So if you ever wondered what an electron looks like, go see an eclipse. Those are electrons you're seeing. It re-radiates the light. When the light comes out, it's coherent with the incoming light and it's polarized because the electric field is reduced by projection. So we can get this angle chi, the scattering angle, from the degree of polarization of the corona. That allows us to solve this triangle down here, right? Here's the sun, here's you, some object scatters light and you see it. By measuring this angle chi through the polarization, you can get this triangle. And you can do that in an automated way. Really neat stuff. These are just some plots showing the degree of polarization for different places on the sky. All right, there's a problem. The problem is there are a lot of polarized backgrounds. The instrument itself scatters light and is probably polarized. We haven't characterized that yet. The F corona is up to 20% polarized. So the zodiacal light, the background brightness that's 100 times brighter than what we're looking at, is itself polarized. And then just to add insult to injury, the star field is polarized. And it's not the individual stars, it's the interstellar medium that's doing the polarization. What that means is adjacent stars aren't random. There's actual structure and science to be got out of the polarization of the light coming from the star field in the sky. We have to remove all these backgrounds in order to get meaningful polarization measurements. And we can do that. We actually transform the polarization state in our pipeline into the various frames of reference we need in order to do background subtraction. Here's an example of it working. We have several examples. This is a more recent one from Matt West. These are actual stereo A, PB, and B images, polarized brightness, regular brightness. They look similar, but they're a little bit different. They're running differences just to highlight the features that we're looking at. Down here is a ratio, PB over B, and over here is the inferred distance out of the plane for low noise pixels. And that's working pretty well. You'll be able to do this with punch data. The noise level will be less, and you'll be able to see the position of more stuff. There we go. This is really just pretty. This is to show you that, yes, there is 3D structure to be seen. This is a movie made by Sam Van Kooten up at Southwest using the WSPR data from Parker Solar Probe. And down here you can see a map of where WSPR was as it goes around a perihelion pass. And you can actually see the perspective of the various coronal features as the spacecraft flies through them. I love this movie for that.
That's awesome.
Is that not neat? That is really cool. So let's let it run one more time here. Here comes the perihelion. Watch the corona now. You can see as we go past things, and they sort of go past us, just like going through tree branches in a forest or something. So that's a taste of the kind of science we want to do by imaging the solar wind and structures within it and tracing it as it comes out. I want to talk about open science. Open science is near and dear to my heart. How much time do I have? Okay. I'll go very fast then. Open science is something that many of us have talked about since the 90s and sort of took the form initially of just open source all of your code and data. But there's a lot more to it than that, right? So the TOPS initiative at NASA kind of formalizes that. This is a graphic from them, and that's on Zenodo. I'm sorry that the actual reference is hard to read down there, but I think you can copy it down. It starts with things being accessible. You can get access to the data and tools you need to analyze and do science. It's reproducible. You can look at somebody else's science and recover exactly what they got. And it's inclusive. That is to say, there's not some elite club of people doing the science, right? You have to allow people and encourage people to come in and do science with you. There are various expanding out. This ramifies. Use open data and software. And I'm not going to read all these, but these are just how Punch is implementing each of these things. We have open access to scientific publications. Open access journals are a big deal. For a long time, you couldn't get access to a journal article without paying $30 to $50 per article. It's crazy. Open collaborative analysis tools. So these are software, this is coordination of data, this is exchanging information. Adopting open source, we're using SunPy on Punch. New pathways to science, try and allow people who aren't in traditional pathways to get access to the process, the data, and the methods, and the collaborations. Let's see, oops, wrong one. Here we go, expanding participation. We're doing that by having ad hoc focus groups, open team meetings, and of course our associate investigator program for young investigators. Foster an inclusive and diverse culture. For this, we're trying to cultivate a team culture of inclusiveness and also to publish guidelines for how people ought to interact, just so that there is a benchmark that people can compare to. Moving from the general to the specific, here's how you can get involved in Punch. Everything is organized through our website, punch.space.swri.edu. We would love to have you working with us. There's a mailing list where we send announcements. You can get on it by writing to that address. We have upcoming meetings where we would love to meet you. There's a winter telecon every year. This year's is 2024, January 23. If you go to the website shortly, there will be an announcement about it, and you can register for it and join. And the Punch 5 meeting will be in June. We're right around Juneteenth. On the 18th, we'll be doing a focus group work on outstanding science questions. That's open. We'd love to have you. And on the 20th and 21st will be a more traditional discussion and presentation framework. So please come to Boulder in June. Go to our website and join our mailing list. Join us. Thank you.
Okay, fine. Okay, thanks. Any questions? That was fascinating, amazing.
What's the latency that you're going to be able to do all the processing in, Craig? Because you're going to want some of these results pretty quickly, but it looks like you've got an awful lot to go through to get them.
So there's a question about how long is the latency? All these things run at the speed of modern CPUs, and so our latency is actually, for the level 1 data products, is driven by the timing of ground passes, about once per day. And we expect to be able to get quick look data up within minutes of arrival, at least of the level 1 frames. We're working with NOAA on a product called Quick Punch that will do a preliminary background subtraction, and we expect that to be available within hours of a ground pass. Then the level 3 data products, I think our nominal latency is 2 weeks, but it'll be much faster than that. There you go, 1-2 punch.
Yeah, thanks. That was an amazing presentation. I'm just curious. You have the PSF that's varying with the field of view, and if you're imaging or looking at regions near the ends of your CCD, and even if you're moving your field of view, how are you going to register your images given your PSF subtraction is giving you residuals, or at least for the particular example, you see a lot more residuals around the edges than the center. Like,
So-
how are you incorporating all of that data?
So I maybe did the pipeline people a disservice by pushing the tails out so they'd be visible, just in the interest of honesty. But the idea is to do the PSF correction so we have a uniform PSF across all the instruments, across all the fields of view. And that's slightly worse than the instruments do at the center of the field of view, but it's better than they do on the edges. And so we get sort of a uniform thing. There are some residuals, there always are, and those contribute to our noise analysis. And so the noise floor is set by some combination of photometry, modeling discrepancies, and unresolved PSF effects. So once we PSF correct them, then we can register them very well. And yeah. Do we propagate noise through the registration process? Yes, we do. We actually track it as a separate pane along with the data product.
Nice talk. My question is quite out of context here, but in the context of imaging science. Now we have expanded our boundaries. We are going with that SECHI from the stereo, then we are going in the inner heliosphere with PSP. So are we planning, or are we thinking about L5 and L4 to observe these features with that different angle and to get more information about the halo structures that are propagating towards us?
So I'm very excited about looking at different viewpoints. It's very important. It is not a be-all and end-all. Stereoscopy doesn't work intuitively with optically thin structures like the corona and solar wind. And so there are limits to how well it can work using naive analysis. But of course, using tomographic techniques and using polarization from multiple vantages, we can reproduce ever more of the three-dimensional structure. So going to L4 and L5 is important, but also these direct 3D measurements are important too.
Can you hear? No, this is.
Yes.
Now, you can hear me anyway without microphone. Excellent presentation. I have comments and questions. So are the measurements that you are taking, is it going to be able to give us sort of magnetic field topology? So if you heard the morning session, right, I'm trying to see how do we connect what you are measuring, just like you showed with stereo. It's the next step. How do we connect it, right? So in order to do better with forecasting, we have to actually understand what's happening on the sun, both weather perspective, climate perspective, so topology, what are we going to do there? And I'll ask all the questions and you answer as you please. I think the previous question sort of asked about, how, importance of different perspective measurements. I have kind of following up on that, what you are taking it might be kind of really interesting to figure out, and we haven't done this yet, but we are going towards that, how to sort the data in AI ready format. And we have lots of people here who are working on very many of these ideas, including kind of, the question that Vishal was asking. And finally, I want to say that India just launched Aditya L1 mission, right? That's kind of like the Soho-like mission with some new observations for the corona, but in situ measurements. So it would be really good. And we have lots of students from India kind of figure out how do we, again, assemble them from a perspective of both discovery science and space weather forecasting.
I'll respond by saying I agree with all of those points. Multiple vantages are very important. Aditya is going to be wonderful. And we have to be very careful and mindful about how we do these 3D inversions. But introducing data to AI is an important part of that. So, will we get topology? From Punch, we will get locations of individual features, and we will get tomography using the kinematic constraints of the inner solar system. Rebecca?
Probably not the question you're expecting from me, but have you talked to any modeling groups about using punch data as an input?
Absolutely, we have. So we have Dushan Ostrasil, who wrote NLIL, on the team specifically to interface with NLIL. And we are reaching out to PSI and other outfits, Cooper Downs and his group. So yes, that is something we would very much like to do. I'll expand a little bit, if I may, which is because we can track features across the solar system, we can calibrate models directly. And moreover, none of us are old enough to remember when geosynchronous satellites started predicting weather. But I know from my parents what it was like when hurricanes weren't imaged routinely, right? Imaging CMEs as they cross the solar system is going to have the same kind of effect on space weather forecasting that hurricane tracking from geosynchronous had on hurricane forecasting, right? We'll be able to see these things as they propagate rather than speculating as to what they're doing.
Maybe I could follow up on that. So if you're going to ingest this data, what is it, a magnetosphere MHD model? What state variables are actually being perturbed or constrained by that then lead on to, say, an improved input into a thermosphere model that would generate space weather forecast?
So what Punch delivers is images, right, which is line of sight integrated density measurements, subject to some perturbation from the illumination function. So what we can deliver is a density structure in the inner solar system. And in particular, we can forecast density as it impacts the Earth, well, retro forecast because our latency is long. But we can provide context for how that density fits into the structures that actually left the sun, right? We don't look at microscale. The things that we consider small are things that an in situ sampler would consider meso or large. And so we see that structure and we can provide a context for how things propagate. In terms of driving a thermospheric model, I think you'd really want to think about the velocity and density functions.
Any other questions? All right, let's thank the speaker again. I think the next speaker is Janet Green.
I'm going to have to take off my mittens. Okay. I'm Janet Green. I'm from Space Hazards Applications. And today I'm going to be talking about some efforts to build commercial tools for understanding space weather impacts to satellites. So I've gone a slightly different path than most research careers. After spending almost 10 years at NOAA, the Space Weather Prediction Center, and also at the Data Center, I now have my own company. It's a small business. And what we do is we develop real-time models of the space radiation environment. We build web applications that allow you to fly your satellite through those environments in real time to understand the real-time impacts. And Lika, when you put up that slide at the very beginning of the meeting with Bohr and Pesher, I think it was Edison, I was trying to figure out which box I fit in, and I think it was a little bit of all of them. So for the students in the room, there are many different paths you can take. So our goal is to create a set of tools that are easy to use, that give you the unique real-time space weather impact to your satellite, your orbit, and your systems. So we're focused here on particle radiation hazards, and there's 4 different types to be concerned with. There's charging, which is when the ions and electrons in the environment either collect on the surface of a satellite, or the really energetic electrons can pass straight through the shielding of a satellite and embed themselves within dielectric materials like circuit boards, eventually leading to an electrostatic discharge that can damage components or make an electromagnetic pulse that can put your satellite in some unwanted state. There's single event upsets, and that's caused by the really high energy ions that can pass straight through an electronic component, leaving an ionizing track. It can flip bits or completely damage that component. And then there's total dose effect. So that's just the slow degradation of all these components due to this constant bombardment by the high energy particles. So there's a growing interest in understanding these effects. I think we heard a little bit about this as the number of satellites on orbit increases. Right now, there's about 7,000 of those. Most of those are in low Earth orbit, but there's plans now for 50,000 plus satellites. So there's a real concern about how to coordinate all those satellites and make sure that we don't have any kind of catastrophic collisions. And impacts due to space radiation are sometimes overlooked in this scenario. But we know an issue for one satellite can become an issue for all satellites. And just as an example, there was a satellite, Galaxy 15, that suffered an anomaly. They lost the ability to actually interact with the satellite and command it. So it drifted through geosynchronous orbit, forcing other satellites to get out of the way to avoid collisions, and also the interference because it just kept happily sending out its signal. So an issue for satellite can be an issue for many satellites, and you can just imagine what might happen when you're trying to coordinate 50,000 satellites. So we've developed a whole different buffet of different models and applications for understanding these real-time impacts. Our focus has been on these ones on the left here, internal charging and single event effects. But now we're actually branching out to develop some models and applications for understanding what's going on at the moon now that there's definitely increased interest in sending humans and satellites to the moon. I'm going to focus here on this model, the solar particle access model, because it's the one that I think is most relevant for the large constellations of satellites in low Earth orbit, and may even be of interest to some of the climate modeling that I heard about yesterday. So the SPAM model, it's not emails about your car's extended warranty. It's the solar particle access model. And the idea is it's an empirically derived, data-driven model for mapping solar particle flux throughout the magnetosphere that you can use to do satellite anomaly monitoring and attribution. I'm mixing up my clickers. So just to give some context about why this is of use, there's a pretty picture of a CME coming out here from the sun. As that CME moves outward, the ions can get swept up in the shock front ahead of the CME and accelerated. At that point, they stream ahead towards Earth. They can flood near Earth space from anywhere between days to sometimes weeks if you have multiple CMEs. There's anywhere between 0 events per year to 23 different events per year. This plot here on the top is showing the occurrence of these events along with the magnitude in red, and then the solar cycle is imposed on top of that. So you can see there's a clear correlation between the solar cycle and the SEP events, but a big event can happen anytime. We're here heading into solar max. There's been 3 events so far this year. One thing to note is the time when most of these large constellations have been launched is well after we've had any of these really large events. So it's unclear exactly what the impact would be once we do get one of those events. And the way these constellations are often launched, it's sort of test as you fly, put things up. If they work, you're good, and then you go from there. So it's a little bit concerning to me what might actually happen when one of these big events does occur. And you don't only need to know that an event is occurring, you need to know where it's actually going to impact Earth. So when the solar particles stream from the sun over the polar cap region, they have direct access all the way down to the atmosphere. But lower latitudes, they get deflected by Earth's magnetic field. So if you have a satellite that's sitting out at geosynchronous, it's going to be totally flooded by the energetic particles. But for some of these low altitude satellites in polar orbits, they're going to go in and out of that high flux region as they go around. So if you want to monitor what's happening in real time and what the impact is to your satellite, you need to know where it is relative to these regions. And that's not easy to do because we don't have observations everywhere, and those boundaries, of course, move as the solar wind hits the magnetosphere and distorts the magnetic field. Which is why we've developed SPAM. So the idea with SPAM is to use actual real-time observations of where these boundaries are and use that to make a global map of the entire environment. So what we've done is come up with empirical methods that allow us to map. Every time one of these low-altitude POSE satellites crosses through these regions, we can map where that boundary is as a function of magnetic local time, and then out to all altitudes and out to all ion species. So every time a POSE satellite cuts through these, we get this full global map of the environment. And then we can turn that into useful effects for satellite companies, which is this LET spectrum, or the single event upset rate. And then we're focused on providing something useful to the end user so they can understand what's going on in real time quickly and easily. So there's an online interface to the model, and you can get the data output with just a few really easy inputs. So you can click and choose your satellite. This is any satellite that's tracked in the NORAD catalog. You can input a start and stop time, and you can select real time if you want the model to keep updating in real time. You can input specifics about your satellite components. You can choose whether you want to see the flux, an LET spectrum, or a single event upset rate, and choose what kind of components you have. And we have a list of sort of common components or input information about your own. And then the tool actually does everything for the user. So it goes out to space track, collects the 2-line elements, creates the trajectory, flies the satellite through the orbit, and then translates that into something like single event upset rate. And then it stores it in a database so you can plot that and visualize what's going on. And this is just an example. This is, again, part of the tool. It allows you to visualize in real time what this single event upset rate is as a function of time. And then you can input information about when you actually saw an anomaly on your satellite and look for correlations and connections between the two, and then continue to monitor that in real time. So we've developed a whole set of different commercial applications for understanding real-time impacts to satellites. So far, we really focused on single event effects and internal charging, but are now branching out into surface charging and impacts at the moon. Do I answer questions now, or do we? Okay.
The next speaker is a student speaker, Observations of Alpha and Ion Cyclotron Waves in ICMA Magnetic Clouds at 1AU by Omkar Dhamane. Hopefully I didn't, you got your name okay.
Hello everyone, I'm Omkar Dhamane, PhD student from India. Here I'm going to present my work in situ observations of alpha and ion cyclotron waves in the ICMA magnetic cloud. Basically, CME is a natural way to remind us how the incredible force is playing in our universe. It is a sun secrets and waiting for all curious mind to decode their unveiled mystery. In the vast ocean of the solar wind, ICME carries a bunch of secrets from the heart of the suns. As we closely delve with the ICME, it has a three substructure: formidable shock front, turbulent sheath regions, and mesmerizing plasma magnetic cloud. Recent decades, the significant progress has been made in our understanding the kinematical and morphological evolutions of the ICME within the heliosphere through space-based and ground-based measurements and modeling efforts. Ideally, it is assumed that ICME flux rope has a circular cross-sections. However, their morphology can be affected by a variety of factors, including the interaction with the high-speed seams, solar winds, or interaction of multiple ICMEs. And this eventually leads to the deformations, deflections, and fragmentation of ICME as they propagates in the interplanetary medium. It's not only alters its visual appearance, but sets a motion into the cascade of events. Such a large-scale interactions disrupt the delicate equilibrium of the ICME, particularly the flux rope. One of the intriguing consequences of such a transformation is the generation of the plasma wave in the deformed structures. Basically, the magnetic force and kinetic force are not in perfect equilibrium, and that eventually leads to the excitation of both magnetohydrodynamic waves and kinetic waves. In the recent studies or in the literature, scientists are dealing with the MHD waves both in the sheath as well as in the magnetic cloud. However, kinetic scale observations or kinetic wave is always challenged. Al-Lahati observed the alpha and ion cyclotron waves in the ICME sheath region, and their study suggested that its occurrence is highest in the vicinity of the shock. But such a kind of kinetic wave is exist in the low beta structures or low beta magnetic structure. This motivates us to investigate alpha and ion cyclotron waves in the magnetic cloud. These are the detailed motivation behind the study. Particularly the AIC waves frequently observed in the turbulent sheath and turbulent solar wind, but there is no precise observations in the magnetic cloud. A spectral break is a common feature in the interplanetary magnetic field. It is believed that it separates a fluid scale from the kinetic scale fluctuations. In the literature, several models predicted for such a spectral breaks, but none of the replicate the observations. And we think AIC could be the best candidate for such a spectral break. Our aim is to interlink a specific turbulent states to the inertial range fluctuations in the polarization of the magnetic field. Now, these are the methodology we are follow for our study. What we done actually, we analyze 401 ICME magnetic cloud event in our analysis. Then we apply a power spectral density to the magnetic cloud region using fast Fourier transform algorithms. Then we apply a normalized magnetic helicity test, which is used to characterize the polarization, whether it is right-handed or circularly polarized or left-hand polarized. And we found that the 14 event, we fixed the criteria basically sigma m, which is greater than mod 0.5. And we found a 14 event which shows a significant value of sigma m. In the next stage, we apply a valence test to use to characterize the check the alphenic behavior. And out of this 14 event, we found a 5 event which showed a significant alphenic behavior. Then again, we apply the theta VB test, which is used to characterize the flow direction, whether it is parallel to the ambient magnetic field or anti-parallel to the magnetic field. And this is the particular event we analyze in our study, which is measured by the WINS spacecraft on 31st July 2000. There is no significant sheath and shock for this particular event. This low number density or low value of temperatures and beta indicates this is the semi-magnetic cloud, which is shaded by the pink color. For this particular event, we observed there is an enhanced, or we noted that there is a high frequency fluctuation embedded with the high frequency fluctuation embedded with the total magnetic field in the inner layer of the magnetic cloud. As we closely observe, there is the outer layer are the free from the fluctuations in the first panel. And this kind of observation only we can see in the 3-second data. 92-second data won't show such a fluctuations. Then, this is the power spectral density of a magnetic field for the particular event. And we observed there is the first hump at the frequency 0.1 hertz. Then second one at 0.6 hertz, which is exactly matches to the gyro frequency. And third hump, or where the sigma m changes from negative to its positive value at 1.24 hertz. Basically, the frequency at which, that is the gyro frequency, there is an increase in the energy, or there is a spectral break, and which is exactly matches with that negative bump in the sigma m. And this could be the ion cyclotron wave, left-handedly ion cyclotron waves. Now check the alphenic existence. We apply a valence test. This is the particular plot in the top 3 panel. We try to correlate, or we try to find a correlation between the velocity component of proton velocity component and alpha velocity component. This positive correlations indicates a strong alphenic behavior in the frequency range of 10 to the power minus 3 to the 10 to the power minus 1 hertz. In the last panel, we shown a temporal variations of theta VB, and we found that this angle is below 40 degree in a magnetic cloud. In the same region where the fluctuation is maximum, we found a high temperature anisotropy. Now this is a spectral analysis. Basically, normalized cross helicity, normalized residual energy are used to characterize the alphenicity. In the right hand side, there is a analysis of sigma r, that is normalized residual energy, and cross helicity in the middle panel. In the frequency which is close to the 0.1, sigma c reaches to the -1, and that frequency exactly matches with the PSD in the first vertical line in the PSD. So there is increase in the energy, or there is a hump because of the maybe inward alphenic turbulence at the frequency 0.1 hertz. Then we try to distribute sigma m, that is normalized magnetic helicity, over the function of theta VB and frequency. And at below 45 degree or 40 degree, we observed that a negative helicity, dark blue strips, in the frequency range of 0.1 to 0.1 to 1 hertz. And this is attributed as alphen ion cyclotron wave is propagating from away from the suns. So this is conclusion of study. This indicates the coupling of fluid and kinetic scale, that spectral break near the frequency 0.6 hertz. And this indicates our study shown that there is a generation of left-hand polarized parallel propagating alpha ion cyclotron wave. The gyro frequency at which we found the energy exchange between the wave and particles. Then what next we are thinking? We are planning to, or we are investigating that whether the transverse propagating or highly oblique propagating wave, kinetic wave are exist in the magnetic cloud. Then how it contribute to the heating processes. Then what are the source of high temperature anisotropy in the inner layer of the cloud? Is it locally generated or from their point of the origin in the solar corona? So the article based on this study is published in the last week in the APJ. These are our collaborator, Professor Raphael, Professor Daniel Telloni from Italy. Then these are my publications, recent publications. And we acknowledge Professor Bruno for giving insightful comment on our study. Also, we acknowledge UCAR for giving such a huge platform to show our research. Then what we are doing in our university department, we are actually working with in situ measurements in various areas of ICME and CIR. Thank you.
Thank you very much. Very interesting. So the next speaker is Immersive Space Weather Analytics by Disha Sardana.
Hello everyone, I'm Disha Sardana and today I'm going to talk about immersive space weather analytics. This is based on my PhD research from Virginia Tech. So I'll walk through the motivation and talk about how I have applied this technique to the space weather data sets and talk about this immersive approach to data analysis. Moving on to a research study that I did with non-experts and then demo with the space weather experts and then findings and future directions. So the motivation behind this research is that whenever we explore data, visualization is the norm. We make scatter plots, heat maps, bar charts, histograms, and it's all in the 2D desktop-based environment. This research is focused on the idea that displaying all these visualizations in 3D environment, how we humans see, we are optimized to see the world in the 3D environment. So what impact it can create, and if it can lead to discovery of any undetected patterns. So the immersive analytics approach enables basically experiencing the data in 3 or more dimensions, engaging multiple senses like sound and sight, leveraging human embodiment, interaction, and sense of presence, and probably just figure out how we can use this approach. So for the space weather datasets, so I picked 3 variables. The first variable I picked is image index data. So on the left-hand side, you see a plot where the red line shows the average image profile of 37 large storms. And in the background, you see the cyan envelope that shows the variability of this image profiles. On the right-hand side, this is the sunspot number, and it's showing the sunspot numbers from years 1999 to 2018. And the pink sphere that you see on the plot, they mark the presence of a solar storm. So right now, I'm just showcasing in this figure 3 solar storms, and the size of the sphere depicts the intensity of the storm, which is mapped numerically to the minimum image index value. Third variable I picked is total electron content. And on the left-hand side, this is a snapshot of enhanced DEC densities during the main phase of a geomagnetic storm. And on the right-hand side, this is the image index data. And the vertical line, basically, it's marked 20 hours away from the onset of the storm. And then at that time stamp, this TC is depicted. So now the immersive approach, basically, you can visualize these structures simultaneously and interact with the data at the same time. So this is the example. This is image index data. And can you play the first video? So in here, I'm using HoloLens 2 device, and this is mixed reality environment. And I have made it to a large size. And this is this image index data. You can explore the data and read the values and find out, let's say, minimum image index. And Perpendicular to it, it's the sunspot numbers. So they are like regionally mapped, and yeah, so you can go through the entire readings. And on the solar cycle plot, sunspot numbers, this is like where this data originates from. And you can see this is an augmented reality environment, so people are doing their own work. And then moving on to the next data set and repeating basically, okay, what's going on. So this is just one way of how I have represented data, and it could be applied in multiple settings. So one thing that this approach can help is with detecting correlations. So over here, I have picked a correlation between the sunrise terminator and delta TC. This figure shows the temporal evolution of delta TC from it, like 24 hours after the storm onset. And the 37 large storms are stacked. Like if you see the y-axis, it's the onset time. And based on the onset time, they're stacked. And if you see this diagonal dashed line, that is the sunrise terminator. And it shows a clear correlation with the solar storms which have onset time below 12 UT. So now this thing was actually, this result came out after huge competitions and using machine learning techniques, and it was detected that onset time is an important feature, and after that this was plotted. So now the same thing using an immersive approach where the TC data is shown and the plane which is used to navigate the time series axis. So day and night time are shown through colors visually. So if it's daytime, the slicing plane is yellow. If it's nighttime, it's blue. And then instead of timestamps, these colors are shown. So it's more like making it more intuitive. And also using sound. So I have used sonification. So for sunrise terminator, so as you saw in the previous slide, there was a dashed line. But in here now for sunrise, you can actually add a rooster sound, or for the sunset, sound of cicadas. And then for the line plots, adding a triangle wave and then mapping it to the pitch so that as the values go higher, the pitch goes higher and vice versa. And this is a good approach. The rationale behind using sonification is that auditory modality is superior in detecting these temporal changes, and natural sounds are found to be relaxing and helpful for data analysis in the past studies. So this is the second video. Yeah. Can you increase the sound? So yeah, again, going through the data sets. So it's mapped. The data is sonified here. And as you cross the sunrise terminator in the local time, you hear that rooster crow, and then you read the data. And as you cross the sunset terminator, there is the sound of cicadas. So this is like making it fun and intuitive. Yeah. So this is another data set. Yeah. So this approach is validated by 50 study participants. They had no prior knowledge of space weather. They had never heard about SIMH index data or TC data or anything. And both of these prototypes were shown to them like after training and everything. And they were asked to identify correlations in the data. And there were two modes, audiovisual and visual only. And as it turns out, even with no prior experience and just like 30 minutes of prior training, they were able to identify correlations of first between SIMH index and solar activity levels, And then for the delta DC, where I use those intuitive sounds, they were able to find relations between that sunrise terminator and how the DC values are changing. And as you can see, the audio-visual group performed much better. So this shows how we can use modalities beyond vision to do data analysis. This demo I also showed to the space science experts at the CEDAR 2023 workshop in San Diego in June. And there were people with different level of expertise. I showed the demo to 42 space science experts and with people over a decade of experience. And I asked a post-study question, there was a set of questions discussing about the design of the visualization and the sound, like if the sounds were useful, if the pitch mapping was useful and such, and most importantly, how often would you use the system in your everyday job. And it turned out the mean responses were around like 4 point something, so that was they agreed to this approach. So the future directions, so this is a new way of doing data analysis, and it can be used for educational purpose, for high school students, for undergrads. It can be used for open and like citizen science projects. And I'm here to discuss with people if they have any data sets or if they believe that this approach can help like these 3D or like beyond vision approach can help them to analyze any of the data sets. And these are just a few examples of like from the feedback that I gathered from the space science people. So yeah, thank you.
So we have time now for questions and discussion. If I'd ask the last three speakers to come back up.
Thank you for the last talk. I just have one remark. So back when I was a graduate student at the University of Illinois, I participated in something in the Beckman Institute, and they built this thing called the Cave, which was a bunch of walls that you could go into and check it out. And I had the experience of wearing one of these virtual environments like you've described, but the example that was given there was the visualization of large molecules. And when there were proteins with interesting topology or loops on one end of the molecule, you could move the molecule and you would be triggered by sound if there was interesting topology on one end or another of the molecule. Then you could move it back and forth. So I really like this idea that you've conveyed here of using sound information combined with AR, VR to explore large but difficult to visualize things. So thank you for your example.
Thank you.
I think there's some development with VR using physics-based model. I want to go into my model and see things because I have to wait for plotting different things. So I totally see that 3D orientation of things. I definitely can see our forecast office can be sitting there and just wander around in a solar wind province, all that measurements. So I think that, is that what you're targeting? Or because I don't see huge potential with just 2D line plot, right? I can see things so well.
Yeah, so I have another data set where I am using 6 different dimensions and I'm using multiple plots. There's a map on the floor and then there are plots on the like multiple sides. So this was my final experiment where I wanted to showcase application, and it was towards the end of my PhD. And the goal of the experiment was to quantify the use of sound. So I wanted to limit some factors there, and it was more like the first step towards using this approach. So it was more like, okay, I wanted to design an experiment that will help me quantify the use of sound, and this kind of approach was needed because I wanted people to go through different data sets and such. So in the future, like I'm looking for postdoc opportunities. That's where my goal is, that using more of the 3D stuff, and not just 3D, but bringing like more variables. There is TEC data over here, there's image index data over here, solar activity plots, or like more variables, and then looking at multiple dimensions simultaneously. So coordinated multiple views.
can I follow on with that? Is there a way to, you're looking at static data, and I'm wondering whether there would be a way to actually have this where your analysis would be interactive, where you could pick a spectral window you want
Right.
to, and then have it actually the data updated real time,
Right.
or that you're displaying. Is that possible?
Yes. So computationally, it's expensive to do. And with the skills, like I collaborated with the CS person, and this is how far we could go. But we utilized voice commands. We utilized zoom in and zoom out features. So let's say room scale size or tabletop environment, or like we did a study with different sizes of the visualizations, and and like doing the real time data, that thing, at least in the immersive analytics, like some people are working on it. So for example, they are recording the heart rate or pulses data, and then that is displayed in front of them. It's just in this field, in here it's not there, but definitely, yeah.
Hello, my question is for Janet. We are dealing with the SCPs. So there are some phenomena called as ground level enhancement, that are GLEs. And for till now, it is not unclear that every GLE is associated with the SCP. So are you going to forecasting for that GLEs also? My second question is, are you taking up the consideration of acceleration mechanism that SCPs have during the interplanetary propagation with the shocks?
No, because I'm really interested in our ability to map out in the magnetosphere less than looking down. So this was specifically for satellites and trying to figure out where they are relative to these SEPs so you can see what's actually going to be impacted. So there are different models that go the other way and look down and to try and understand impacts to airlines, but that really wasn't our goal.
My question is also for you, Janet. So you should expect this from me as the open science person. But as a commercial company, do you see open science as a threat to your business model? Or I saw the interface. Can you explain your approach to this whole movement?
I've never seen it as a threat. I think every time you interact with someone and make something open, that just makes it grow bigger. So I have implemented one of my models at CCMC. I don't have any issue with that. I've never had to worry about someone taking my idea because I always have 10 more. And usually it's not the idea, it's the actual doing that is the hard part. So it's not really a concern.
My question is for Omkar. That was a very nice theoretical presentation. It kind of flies over most of our head, but that was good. And what I was thinking of, how are you trying to validate the models, right? So are you going to be using any kind of data to actually, show some level of validation, or data don't exist? And in particular, I was curious about Aditya L1. Are you trying to integrate some of those observations?
Yes, actually, we are working on in situ data. Basically, a lot of theories are predicted for the spectral break. Different models are there to predictions for the spectral break, but none of the model can matching with this spectral break. In solar wind, I think Bruno and if I'm not wrong, Bruno and Teloni found that exactly that AIC could be the best candidate for such a spectral break. But these are the observations in the solar wind, but not in a magnetic cloud, because solar winds, it's a turbulent solar wind. There is a possibility of such structures, but in magnetic cloud, I think there is a rare in case of magnetic cloud. Is in the context of Aditya, and we are waiting for the Aditya data, eagerly waiting for to analyze the data and everything. Thank you so much.
So first, I just want to shameless advertisement. So I don't know, James come from University of Illinois. I was a grad student at University of Illinois, and my PhD advisor has a Raluca Ilia. She developed an immersive learning lab, like focused on using the VR technique to learn the electromagnetics. So basically, like build a story for each Maxwell equations, and the undergrad can learn what is electromagnetism inside the VR lab. And I do agree with the sonification idea, and I like how you choose the sonification choice, because I was sitting in a solar physics seminar recently, and they choose the sound near like noise. And but there's a benefit for that. So according to the speakers, it took them 2 hours to listen to 1 year Parker Solar Prop data. And based on the results, they can identify the regions that is not originally explained by the solar physics mechanism. So I can really see that there's a lot of potential in the VR technique. So just want to say a few words about this.
If you can put some of these links on the Slack channel, what's actually publicly available, right? That would be awesome. Thank you.
Another question?
Thank you. This is a question for Disha. Very nice experiments, and I like the statistics. Did you have any control groups? Like, how do people, uninformed people, without sonification, are they able to find these correlations, or what fraction do they find of them, are able to figure these things out? Do you have a control group?
So I collected participants' demographics and I collected their prior experience, if they had any experience with sonification or not. And I did not find any statistical significance over there. There were out of these 50, and then there were 4 pilot studies. So out of 54 participants, there were, I think, about 3 people who knew about sonification before. But I think what matters is the design of the sound, and if you make it intuitive enough, and if you train the participants. For example, pitch changes, those are easy. Like, we do sonification in our everyday lives also, we just don't know it, that it's there. For example, you're driving, you hear the car beeps, it's an event notification, so you hear things all the time. So it's easy to train them. So even without any prior knowledge, they were able to pick up on things.
This is for Omkar. Omkar, nice talk. All three of you, nice talks. Omkar, the event that you showed is no shock, no sheath, but a magnetic cloud. Probably it's a flank cross.
Yes. Yes, actually.
So, do you really see this typical phenomena for where you can see the 3 typical ICME properties: shock, sheath, and a magnetic cloud
Yes,
properly?
actually, I have more events, 4 more events where for means you're saying for including shock, sheath, and magnetic
And
cloud.
magnetic cloud.
I have the same signatures. I will show you later.
Then the cross question is, then why you are showing this event than the other events? I mean, what's special in this event?
Actually, the special in this event, the particularly in the, you can see in the, I think in the PhD plot, you observed it 3 hum. Basically, this is the event where we observed a inward alphanic turbulence at a frequency 0.1 hertz. Basically, so that's why we shown this particular plot.
All right. So I have a question for Janet. On some of your plots, I thought it said sort of single event upset rate of per second. Like, that sounds like a huge number to me. I mean, satellites can tolerate having bits flipped more, several a second. Is that, or what does that mean for operations?
No, it wasn't several a second. I don't remember what the units were on the plot. But there are a lot of corrective things that go on, and there is a certain rate that they design it to. We haven't looked in detail. We struggle with getting information back from users about the actual impacts that they've had. So we don't have a really good validation yet of what we're putting out.
So yeah, this one is for Janet, kind of, going back to the moon, basically deep space exploration. It's a different kind of radiation hazard. And I guess, how far along are you? You talked about spam in the magnetosphere, which is where, a lot of our satellites get impacted. But from the point of view of radiation with astronauts, and spacecraft in deep space. How far along are you with that kind of modeling environment? What is your data source for SCPs? Just curious.
So the tool that we're developing for the moon is really more to evaluate surface charging effects. So I'm part of the science team for the Hermes instrument, and we've started with the Themis Artemis satellites to try and characterize the charging environment and what the impact is specifically for Gateway. So we can develop a real-time nowcast model of what the expected charging would be, which generally charging in the solar wind is not a huge issue, but with Gateway, they're talking about docking maneuvers and things like that. So it may not be an issue, but you don't want to do the calculations once you find it is. So we're doing that now.
Any more questions?
I just have a question for Omkar. Please, when you were introducing your work, you mentioned ICME to ICME and ICME to HSS interactions. I just wanted you to throw more light on what is the difference between these two interactions.
Actually, ICME HSS interactions and ICME ICME interaction. In case of ICME ICME interaction, there is a chances of merging of cloud. But in case of ICME HSS interaction, I analyze one event. I will show you. In that particular case, see the particular definitions or particular definition of the magnetic cloud is that when it get expand, there is a decrease in the magnetic field. I have that. I analyze that event, which show if the ICM HSS interactions occurs, there is a rise in the magnetic field, which is completely contradictory to the conventional definitions. So there's difference.
That's a question for Janet. Following up on the lunar measurements, are there plans to have surface charging measurements on the surface of the moon? Because we're somewhat concerned that when the moon's in the magnetotail in particular, which is, I don't know, several days of its orbit every month, and we have a large geomagnetic storm, there could be significant 100 keV electron acceleration back towards the moon and possibly collecting on surface equipment.
I think there are, but I don't know the details of what's going on with that. Sorry.
So part of my Eddy proposal is to look at the moon. So I'm working with a group of the Artemis team right now in Berkeley. We do have a huge amount of SEP particles in the magnetotail. Like the magnetosphere is not enough to show the SEP, so they would penetrate through the magnetosphere. And they published these papers recently, so you can check it out on GRL. Oh, and for tail electrons, that's my project, so I can talk about it. So there are two things. One of the ions can come from the Earth's ionosphere. One of the ions can come from the moon itself. And it was a debate on which one is important and which gonna be energized. But honestly, right now, the Artemis or like the Themis or like the existing observation data, they don't have sufficient IMX spectrometer to answer these questions, or their plan, like orbital plan, is not enough to explain these questions. So that's how I'm gonna do in my postdoc fellowship proposal. So, yeah.
Okay, if there are no more questions, we'll have our lunch break now and reconvene at 2 o'clock. Thank you.
Subswarms, basically. So
It's a model, but it's an LLM model, so it's fairly accurate. Dynamics. So here's 20, 40 moves at 60 RE. This is why I said but yeah, no one's measured. Nobody's really realized what's going to happen. It's easy to kill electrons that take out oh, this is oh, we know that's precondition. So a substorm. I hate this. Okay, so what's going to happen? That's legit. Classic super here and Europe is here. This reconnection jets, electron jets. So this one event in itself causes well, these electrons go down the magnetic field lines here, across the Auroras, and these electrons go back here. But the moon has a magnetic field, so it's just going to be it's like a satellite covered. That's the question. I think it's like 10 to 100 keV.
Well, like, so, for this kind of
We're not actually worried about the moon. Now, on the moon, but the space station is made out of metal. All those electrons are getting collected on that space station. That's like they're doing satellite. So these things make satellite and geo. This is what kills the satellite. Surface charging. Surface charging. Your satellite is all of a sudden covered in electrons, and it can't ground properly. They discharge. So you get these big light strikes, you destroy the satellite. So what's going to happen with stuff? Yeah, it's really interesting to see what yeah. Okay. It's going to be we don't know. That's the question. So that's going to be interesting because we are. Exactly. But if you're doing it constantly, you probably won't catch that's the idea. Yeah, I got a PhD in 97. That is you. Yeah, this was way back in the day. They never full walls and ceiling. Yeah. I really enjoyed going through there. These really heavy glasses that are like. But no, I didn't see it. I was there when precursors of Nancy. So I was like learning tag and playing with that was a multi. Yeah, really good. That's what I've heard. Yeah, I'm thinking about a bunch of other things.
Oh, yes, not forgetting the David Dobbs. So you have
I mean, the surrounding buildings, I guess. Yeah, I've been back. I started, I think it was 2010, right back in 2012. I served on like a review department. Yeah, but now you're Berkeley. I did my postdoc. We're following each other's steps.
I don't know.
But I really like
Okay, so, I'm sorry, I was imagining, I was trying to take it down the side.
Will you grab me that? Actually, I was thinking, yeah. I'll take your meeting again.
It's a big experience. And all of you who have mentioned, when Disha died, you should our backup has. Oh, it's possible. Okay, let's I know.
They're great. They're doing really good. Okay, so at the hospital tonight, they're doing a Mario Brothers theme. And all the kids get to race tricycles at the hospital. So yeah, just super busy. Even though I didn't go on the trip, I'm just
Good, awesome.
Yeah, this feels great.
That's really helpful.
Yeah, feels great. The snow, I was not ready for it.
No?
No, it was 8 degrees that one morning. Well, are you here today?
Yes.
Yeah. They run it at 10. I sent you this. Yes. I was thinking we could meet on 6,000.
Yeah. Sounds good, right?
So I'm off on Friday. Yeah. Friday, Thursday.
Take me back to a time when we didn't have a way.
Sometimes it feels like the world is ending. We're just a flicker in the universe. I think that we can stop pretending like everything is fine otherwise. Sometimes giving in is happy and sad, but running leads us further to nowhere. And we just got too tired of defending. So time and time again, we gotta learn. It's darkest before dawn, so don't give up. Just say it's on. Oh, don't give up. 'Cause when the morning comes, it all feels like a dream. It's darkest before dawn, so don't give up. It's darkest before dawn, so don't give up. Just say it's to the sun. Yeah, you said. 'Cause when the morning comes, it all feels like a dream. It's darkest before dawn, so don't give up. I got something. Yeah. Oh, really? Yeah. Sometimes something else is taking over. Like we are getting somebody to the show. Somehow living life in slow motion. And where we go, we don't really know. It's darkest before dawn, so don't give up. Just sing us to the song, oh don't you stop. 'Cause when the morning comes, it all feels like a dream. It's darkest before dawn, so don't give up. It's darkest before dawn, so don't give up. Just sing us to the sun, oh don't you stop. 'Cause when the morning comes, it all feels like a dream. It's darkest before dawn, so don't give up. It's you, it's always you. It's all never gonna fall in love. Always gonna be you. It's you, it's always you. I don't wanna be like nobody feels like you. So don't break my heart, don't tear me apart. I know how it starts. So I've been looking for, don't break me again. I can live again. Please don't break my heart. 'Cause me, I've been broken before. I have been broken, yeah. I don't know how it feels. So don't find out your love is over. I'm still hurting, yeah. I'm hurting inside. I'm so scared of falling in love. It's you that I try. It's always you. Fall in love. It's gonna be you. It's always you. I don't wanna be like nobody feels like you. So please don't break my heart. Don't tear me apart. I know how it starts. Trust me, I've been higher ground. The race is on, the clock is ticking, so far behind. If I keep stuck instead, take a break, let it out. Here, but I'm not there, just afraid in the crowd. I'm always chasing time, it's never on my side. Wish I could make it right. Someday I hope I'll find a little peace of mind and leave it all behind. Another night, I'm overthinking. So many thoughts are going through my head. I make mistakes, I'm only human, but it's not enough. If I keep stuck instead, take a break, let it out. Here, but I'm not there, just afraid in the crowd. I'm always chasing time, it's never on my side. Wish I could make it right. Someday I hope I'll find a little peace of mind and leave it all behind. I'm always chasing time. I'm always chasing time, it's never on my side. Wish I could make it right. Someday I hope I'll find a little peace of mind and leave it all behind. I'm always chasing time. Everybody knows my name, but something about it still feels strange. I'm looking in the mirror, trying to stay yourself and take somebody else. Everything is not the same. It feels like our life changed. Maybe when I'm older, but I'll go now, but it's coming up. What if you had it all, but nobody to call? Maybe then you know me. 'Cause I've had everything, but no one's listening. And that's just fucking on me. don't know, and I don't feel down, but I don't know how. Turning all around, all of the nights that I've spent crying, missing you all alone. Wishing that I could hold you tight, hiding back at home. Give me your love and don't let me wait in vain. Just give me your love and give me your love and don't let me wait in vain. Just give me your love and now it's clear. After all these years, after all these tears, you were never ever here. All of the nights that I was spent crying, missing you alone. Wishing that I could hold you tight, hiding you back at home. Give me your love and don't let me wait in vain. Just give me your love. Just give me your love. Yeah.
Yeah. Did you have lunch already?
So you're going back to UK after how many years?
25. No, more than that. 25 in Boulder, or 24 in Boulder.
That's a big move.
Yeah, more like 40 years.
You're gonna have a hard time with this.
I've been going back and forth for the last 5 years, teaching. So I've been spending 20 weeks a year there for the last couple of years. So I know what I've been doing at Eddy.
My son lives in Western Colorado, but he spends most of his time in London. He runs AI for Palantir.
For who?
Palantir company. He does machine learning AI. But he lives
In demand, I assume.
Huh?
In demand.
In demand, quite a bit. But he likes his teams, so he lives here.
So is he employed by a U.S. company or by a London company? Just working remotely?
No, Palantir is an American. But the degree of talent they get in machine learning in London is significant. So they maintain the lab or it's a great place to be.
I did for a few years in London.
Yeah. I was spending more time in India those days. My parents went back to work at India a few years ago. Now the chances of coming back are zero. They're not getting any language. I don't know the choice but to.
Well, that's what happened. My father's still alive, so he's in the UK. So that reason to go.
Yeah. Well, good connect. I heard that there is a chance of moving in India. That'd be great.
Yeah, this time next year. This is what Lika says. How long is the flight from San Diego to Kenya? How long is
It takes me 40 hours before I get home. Minimum. Sometimes 50 because I have to go to the town locally.
Yeah, for me it's 24 hours roughly.
Yeah, so good thing is I don't get jet lag, so I use most of my time. So the work doesn't stop. It's just that the people around me go crazy. Right? So, because I come for 2 weeks and I go there for a week and come back. But yeah, it's, people don't expect you to cut to India every month. That's on top of the other people. That's
Well,
you
must get a lot of upgrades if you're flying that much.
oh yeah, I'm a special guest at most airlines. I think I have 20 million miles status in America, million miles in miles is not a problem, yeah. Just like
The main problem is if I'm in the US and I'm getting up to get on the phone or on Zoom for 7 a.m. calls. So when I'm there, in the evening, everyone wants to get on. So it just makes the days really long. There's no time for anything else.
Yeah, so my meetings are like at night or late night. And from phone point of view, I actually carry 2 phones. One India, one this, it's Indian number. And it turns out phone telephone stations in India is so much cheaper that I actually have a plan working here.
I have 3 phone numbers on here. I have 2 eSIMs and 1 US one.
There are 4. There are 2 eSIMs and then an Indian SIMs.
So, yeah. £10 a month.
Yes.
Unlimited text and 20 gigs of data. Sometimes.
Yeah, my plan is like 2000 is $40 a whole year. I mean, it's 110 for what agent. Anyway, I'm gonna go.
Okay.
Take care.
You're heading to the airport now? Or?
Yeah.
Okay.
Attending the school of including in data science. Physics and theory. That's a big deal. Take care.
Yeah, good job.
me in the corner. That's me in the spotlight. Losing my religion. Trying to keep out with you. And don't know how to do it. Oh no, I've said too much. I haven't said enough. I thought that I heard you laughing. I thought that I heard you sing. I think I thought I saw you try. Oh, life. It's bigger. It's bigger than you. You are not me. The place that I go to. The distance in your eyes. Consider this, the end of the century. Consider this, that nothing to my knees bear. Like all these fantasies come flailing around. Now I said too much. Oh, life is bigger. It's bigger than you. You are not me. The place that I go to. The distance in your eyes. Oh, I said too much. I said, oh, life is bigger. It's bigger than you. You are not me. The place that I go to. Distance in your eyes. Oh, I said too much. I said, oh, life. Wake up, the gates up, taking a rising sun. This time of darkness is set to run. Some in the sky, it's amazing. I saw my car and I'm leaving this town. I don't have no one to save me. I lost my phone, it don't faze me now. My soul is free, I run. Yeah, I can't take to my heart. 'Cause I long to feel my lungs. They say I'm crazy, I keep moving on. 'Cause I'm living my life under the sun. 'Cause I'm living my life under the sun. It's a new day. Under this golden sun, I found a new way to give you all my love. Yeah, I brought this desire.
your glow stick there? Are you sure? Because I saw you hesitated for a second. And everybody needs a glow stick. I had Andreas take some of that, had like some spider rings that glow out. He's gonna take his daughter after the vacation.
I don't wanna walk 'cause it sees me. I lost my phone, it don't face me, no. My soul is run. Yeah, I can't
Yeah,
I don't feel my life. They say I'm crazy, I don't know.
Just a yeah, that's what Mom was saying. She said that. She said that.
My soul is run.
I just want to stay out of any drama.
They say I'm crazy, I keep running on. Cause I'm living my life.
I wasn't volunteering, so.
No, it's just like this.
Oh, that's a problem. I just, yeah, okay, so let me write that down. So that's Thursday? Yeah, right. Thursday. All right, because he helped some yesterday with yeah, he helped with, breakup with the trade. Right. Yeah.
No.
Are you gonna do some Halloween dinner?
Yeah, work related. I don't know, but yeah, it's not eating rugby because it's not. Yeah, so.
I was hoping you were gonna tell me something fun.
No.
Yes, I'm going to a costume ball. And I have the best
I wish.
vampire outfit.
No, I actually this evening we're gonna have to do the other story.
I'm so sorry. You might want to take a handful. Yeah. Have to get a little sugar.
Actually, the glow stick might come in handy in that direction.
For real.
Oh, boy.
Yeah, I'm too many people. But
Yeah. Okay, when I see, Lika, I will talk to her about these two things. We have a third thing. Yeah, so. Yes. Well, no, there should be, it'll tell you. It does. Okay. But what's the meaning of go to any? Yeah, they're all, it's all, yeah. Good. Yeah, good luck. I hope it goes all right. Yeah.
give us the patience we need to make it through. Just hang on and you'll see. I'll show it all to you. 'Cause anything worth
How are you? Starting to get at 2. Oh, yeah, great. I'm thinking about getting this for meeting next Sunday. Oh, I see.
So give us the patience we need to make it through. Just hang on and you'll see. I'll show it all to you. 'Cause anything worth having is worth fighting for. Every day we're stronger than before. And the world keeps spinning on. And I'll stay 'cause I'm sure you're worth fighting for. Anything would happen is worth fighting for. Stuck out for lights down. Do I breathe?
Yeah, the first two. Mine is actually smaller. Oh. All right, hello, my name is Medina. I'm a first year African Americans, and I'm an organization scientist. And today I'm going to be talking about how citizen science is impactful for the field of good. This is the wrong All right. And today I'm going to be talking about citizen science in the field of good physics and how it is important. First of all, what is citizen science? Well, here's a working definition. It's organized research and the public leading process of scientific investigation. Answer questions about data and the results. There's 10 defined citizen science, science association. But basically, citizen science projects which aim at more of an organized collection of data for participants. Then you also have grassroots efforts, which is kind of what I'm talking about today. We're chasing citizen science for those things. But there's a lot of government in this place that make sure that what they're doing is actually impactful. So citizen scientists are agile collaborators and using the Aurora chasers as sort of a model for this whole principle here of scientific agility. So, we all know what agility is in terms of athleticism in the scientific context. It's the extent to which a person can be able to help their progress and efficiently adapt to adversity as opposed to people that progress as well. Having a project that has a lean scientific team that can respond and pivot quickly to the needs of the users and citizen scientists is important to making sure that you can hit your goals. And inevitably something's going to go wrong and you can adjust things. So being agile is important. So citizen scientists themselves are also agile. They're unbiased worldview. Everyone has their biases, but they're not biased scientifically. So it's important. They can identify things using their innate abilities as humans. Trained to look for patterns, but specifically the word chasers know what's important to identify precision years ago for mission velocity enhancement. And people are naturally tuned to classify things as well. And word chasers like to call Auroras certain things like cinema Auroras. One term for spiral Auroras, which are actually significant for scientific study, but Auroras chasers have their own names, are just natural things in their everyday life. It's just discovered by Aurora chasers in Alberta, or rediscovered. It's always better than brought into more life by Aurora chasers. We're also producing scientific development data. So, citizen scientists are, I would say, naturally tuned to producing scientific development data from that data, time, location, exposure time for photographs. Things like that. And that means that the data that's coming out of citizen scientists are used for scientists. See that being incorporated in citizen science goals here. These data have to be process, but not too much. Citizen scientists also bring a lot to the table in terms of their expertise. There's really two types. There's contributory and experiential. So contributory essentially means that public scientists sort of stand on this ivory tower of excellence and think of everyone else as below them. But in reality, a lot of people are skilled, they do their PhD in languages and advanced degrees in other fields. They just don't have the context and fancy statements like that this year. When they come to projects and when they submit their data and they can talk to scientists, they can bring perspectives from their own lives. Also, educators especially have experience.
And then there's also
Hundreds of thousands of times I've seen the Aurora times. And that gives us a unique skill set in knowing what's normal. So scientists know what the outside imagery and statistically determined, okay, I can see this phenomenon 10% of the time, and that's rare. But you can ask somebody who's able to change the same question and tell you that in 5 minutes, whereas scientists might take a month. This is not actually there. But they also bridge professional science and the public. So scientists are always trying to engage the public and show our research and inspire people. Well, you can do that through citizen science. These participants are very engaged in science. They have this curiosity, and they can take that back to their own communities and sort of help spread our own message in their work. So a lot of it is translating the science just so the public understands. Citizen scientists are kind of like mediator in that whole system. This little flow chart that published this year on citizen science, it sort of shows how you can use forward-facing communities with positive feedback to drive new discoveries and the inspiration sort of keeps everything going.
So pretty much.
And there's lots of projects that are doing this. So, for example, Auroras, project that I worked with in the past. And essentially, Auroras is a platform.
So we just have that whole house.
Prediction of elevation defined model. And essentially what that does is it provides the ground truth value of what we're seeing in the model, because not all the time does the model line up with predictions. That's where the science can come into place. You have these, these storms where the models are going down in Minnesota, North Dakota. You've got some science photos from New Mexico, Arizona showing there's Auroras. So obviously in the models where the Auroras really setting through. And Aurora Source is an example of a project that facilitates agile collaborations. Not only does the platform itself sort of facilitate users to submit their own data, which already exhibit all the qualities I talked about being scientifically useful, but there's a master program which helps facilitate the connection between the public and scientists. And there's also educational content on their site, which provides more information for users to become not subject matter experts, but more expert in the field of space physics to help train them to be better citizen scientists and contributors. This is sort of the broad overview of projects that are doing this as well. There's a huge suite of citizen science projects in the NCAR portfolio, and over the next year we're going to be seeing a huge push towards delivering these projects and boost them up with the geophysics big year, which is started in the summer, but our groups it started this summer with the solstice and next year with approaching the sun. And that goes into the courses. We just had one this month. We have a total next April 8th. So citizen science projects are going to do a lot. We've got a lot of really unique data. There's more sorts down here, but we also have others like that. Solar control, spectacular, something to watch at Freedom Spotters.
No, I'm talking about trying to engage.
Projects are agile and help leverage citizen scientists and make our science better through that. Just concluding here, really for this is becoming increasingly technology-driven and collaborative. So this is kind of where the push-pull comes is at. And the community models looking at bigger data sets and reconciling these really interdisciplinary problems. And one way to solve it is through citizen science, because those people are not preconceived with a certain project. They can approach a scientific problem, but or not as much bias as we would. And we use this in science as one solution to these problems, solving current challenges that we've been facing decades ago. And the agility in science in particular helps us solve big problems, helps us engage in problems, inspires others to join our field, scratch multiple studies that bridges disciplines, have programs around heliospace as well. So all these different bridge those gaps. And also bridge them in ways that you might have not thought before, and for considering citizen science for your next project, there's a number of calls here. Roses that you might be interested in going to. There's some seed funding open, that's just a little grant. There's some big 3-year grants that's accepting applications. So with that, thank you for your attention. Here essentially my own passion for working brings the scientific community to share.
So, I would say 10 minutes on the
okay.
First of all, you're not then second,
I hope so. I'll probably be wonderful.
Maybe again, right?
No, the rambling definitely. The rambling definitely overshadows other sheets. That's right. I'll practice it. Just feel like that we have the slides.
I also feel like if I get mine something.
Oh, we can do that.
Someone either things are very clean, things are great, and we can make sure the results. So I think there's that level of trust and building and the urgency. So SUPSI messed up. Every model is different, every model is different. Because we voted on community, we just plug it in because then as long as we can make model diagnostics successful. And now that it's not good, just say analyze things. I just don't see we have the research. For specific perspective, maybe not working. Just we're already so in. Just don't have time to play. We love that model. Most models carry. So we don't learn it all ourselves. And there's no way to stick with that. Community, and I have to go through this on this. I just got laundry, so they say your body got laundry. So we change our plot.
But I find is that you can exhaust it for something to
Exactly, whenever I want to hire an operator, how am I going to find somebody to use somebody undergrad who graduated out of school that is able to train.
Yeah, no, I was supposed to do that in practice.
What else promotion do you need? Are you happy with the salary? And make sure you nice enough. If you had to leave, you told me early, like a year ago. And he's seen the space industry, we talked about spaces. I can tell you, maybe I can tell him, let him tell you what he did.
It's
So he can jump there with 3 times salary. It's that resistance. I think our operation is really tied up in 1 or 2 things. Like, I know where it's every day. 2, 3. But Jim doesn't know how to run it. So it's like, yes, 3 people in the room is running the whole thing and knowing what it means. Just throw it away and get it. Let's get whack of it.
Right? So at some point, Myron Boulder is going to be using the model. And I think, yes, I think 10 or 15 years, and plus. They're going to start thinking back to design the market.
They have start thinking, am I going to be tired at that time? I'm retired 2 years. So I don't know, it's your problem. Right? So when you still have parts, you can talk about it. It's easier, so.
Every time somebody says, oh, yeah, it's not, they stop thinking about how much of that is boring plumbing and making sure that everything works and everything's connected. And nobody gets excited by fixing it. Right? And so they end up, oh, I'm going to do this thing here for Thursday, I'm going to do this thing here, let's do this thing over here, and it's just going to be machine learning, and they have all these little things. And then somebody says, oh, no, we're going to actually make a model. And they go, yeah, the point of
Whoever is in our field doesn't want to do a solving job.
You can say, okay, there's nothing to do. In which case, yes, it's going to happen. Right, or you can say, no, we are going to do it very easily, we're going to do it eventually. But by extracting what was doing it bit by bit and ending up with a much better
It's a way of physics package. Yeah.
I didn't know that.
Yeah. Right?
God.
Yeah, it's the CCP. What it is you take your code and you put ASCII headers on it, which say what the inputs and outputs are. There's a preprocessor that then reads that in and does the function. It's technology that is 30 years old.
So you know what we do? We just pull out quantum physics and put it in.
This is our new thing to say this. Yeah, this is, I mean,
you know what we did?
Some technologies from 30 years ago.
But then what we did is we just pulled all the physics.
Right. So this is what they did.
Right. You can all the different things. Yes. It's like a swap the sun.
more physics, boom.
Because I need to make progress next year. How do I have time to suffer all the way in class?
When it is a then you know you take something other. Where did you know that you could go change the plan objects? Did you know that? Did you know that? And because they're all, it is everything is dependent.
That's not go-to statements and you didn't use them, and you couldn't trace them.
That's the thing, right? That is
so that we trigger that.
There is. If you go look at the main times that in these special things where you start where you start it's no wonder it took a grad student 3 or 4 years to try and get harmonies, and now it's probably going to take 2 years to turn it into something like into so there's a student it's been this organic thing. You don't even do process. I want to know physics of other forms. I said, screw it. I'm going to go out on spot.
So like choose how to do you choose how to use your time.
How far it runs to CSM would be exactly so
if you want to rise, you want to have one condensing species, you want to have dust, you want to have like, you have to have all the elements, you can't just go back to residuals.
So there, when you build them up, you get certain physics. Right? The problem is you only have everything or a very simple model. So in order to build physics or a model, you want to start with a dipole, then you start putting your units, right? It's much simpler. Inherent and all the very specific stuff.
I have to go to that version. I don't know it works, right? And the only way that it works is that you go through everything and you say, okay, where's the most specific thing? And then you containerize that, and then it's like, okay, now I have a variable that is relevant for a different planning or a different calendar. And we went through every single bit of it. And where there was something that was thing, we just made it into a variable. It's in the parameters or parties. And then we have one piece of code that works for everything. And we haven't had to try it.
The point is you can build that where you can tear that for change. So there's so much and even if you wanted to start at something so the easiest thing is to start from
So go into it and see, hey, why doesn't it work when you have the goes to zero? I have no idea what to do.
So you can tell people the thing is,
no, I think
this is what we're doing.
This is not really this is something we can decide to change. Yes, that's not so. This is not
They always interpret it as, oh, you want to play, but that's not. We're not asking them to get their own certification. That's the science. That's the science. So yes, you want to go that is like Mars. So all the hard, everything that's hard to do is first constituent. First element is water. Second one is so yes, you could go ahead or this is what we do. I don't really want to. And then you have a case where 1, 2, 3 is rather. And then you have another case where it's 1, 2, 3 is come downside I'm interested in whether or not I do not need to. First of all, get them all back to stay with all the physics of Mars before you run the first time. No, these are oh yeah. We're having some intense conversations here. So, okay, sorry. So, the first speaker is Natusha Kuroda.
Natsuha.
Sorry?
Natsuha,
sorry.
That's okay. Nobody gets it first time. Thank you. All right. This is my cheat sheet, so sorry. Okay. Good afternoon, everyone. I hope you're not falling asleep. My name is Natsuha Kuroda, and I come from Naval Research Laboratory. And I am working in a group that's building CCOR, which is here. It's a series of compact chronographs for space weather forecast. Oh, sorry, that's the wrong one. Yep. Okay, so we all know that coronal mass ejections are one of the most important space weather phenomena. It's the outburst of solar plasma and magnetic field into the corona and its interactions with Earth's magnetosphere-induced global scale perturbations that affects Earth systems such as electric power transmission, navigation systems, radio communications, and satellite operation. So let me first ask you, how many of you heard the CCOR before you came here? Okay, few. How many of you have heard LASCO, SECI, or seen these pictures? Pretty here. Right, that was what I was expecting. So CCOR is basically a successor of these two famous white light coronagraph in space, LASCO and SECI, but it is a series of smaller, more advanced coronagraphs that are designed for easier deployment on a wider variety of spacecraft for the use of operational space weather forecasting, as compared to more of a research forecast satellite that was LASCO and SECI. So this is a little diagram showing some design difference. Top is the SECI Core 2, and this is CCOR 2. Basically, the sun is here, and you're shining light in here. There's a lens that focuses the sun's image in the occulter, which creates a little eclipse, and then it will go through another lens to mitigate the straight light that comes from here, and it projects the image on a detector. And that was the previous coronagraph design, which needed this long optical tube to house this complex optical structure. But for CCOR, we have a more sophisticated design, especially near the occulter here, that has a lot of disks behind it to mitigate the straight light instead of this structure. That makes it possible to be shorter so that it's easier on a variety of spacecraft deployment. And the point is, though, all the while, it achieves the same level of diffractive straight light rejection as the previous instrument. So it is as good as it was for science research as well. Okay, great, the movie is working. So this is the simulation of CCOR images produced by scaling real LASCO C3 coronagraph images to the brightness that we expect from CCOR. So this is the famous LASCO movie, and it's a CCOR simulation. This field of view is in scale with each other, and as you see, the CME signal is clearly seen in here, and it is readily detect CME within this FLV. This is the table for those who are interested in looking at what the requirements are and the actual spec from the previous satellite LASCO. And here you have some FLV difference here, which is a little smaller than the LASCO C3. I want you to see this cadence here, this is operational satellite. So it's 15 minutes. It's a constant image interval in order to capture the fastest CME possible in a few frames of this required FOV. And it is notable because in the previous satellite, it was not constant. It could have varied from 6 minutes to hours sometimes. And so this is one of the key features of the operational satellite. But the photometric accuracy, which is equivalent of signal to noise ratio, and the minimum coronal intensity that it can detect is preserved as equally good as the previous instrument. So CCOR is planned to be deployed on 3 different spacecraft. First one is GOES-U, which goes to geosynchronous orbit on 2024, next year, April. And CCOR 2 is going to go to L1 on SWIFO, Space Weather Follow-On Satellite, in 2025. And CCOR 3 is planned to be on visual by ESA, and it's going to go to L5 in 2029. So why do we want to have SEACOR images? Sorry. So we have this space weather forecasting model at NOAA. This is famous WSA Enlil heliosphere model. The space weather forecasters that use this model use this chronograph images to create the 3D CME model to deduce these important parameters, CME width, mass, velocity, and direction, that gets fed into this heliospheric model, which then predicts the CME arrival time, intensity, and duration, which gets turned into geomagnetic storm watches that get to customers such as industries and power grid operators and so on. So LASCO and SECI has been providing these images to this tool, and SEACOR will inherit that tradition. So for the sake of this group theme, risk and resiliency to space weather disruption, I'm here listing some important features that CME imageries have contributed in the space weather forecast. So, for example, one publication said the CME imagery from coronagraphs have improved successful geomagnetic storm forecasts from 27% to 60%. Another thing is arrival time uncertainty. Having CME imageries in the space weather model have reduced it from 12 hours to 7.5 hours. And another important point is that we need to have multiple viewpoints in order to reduce these arrival time error as much as possible. For example, one publication said that having 3 viewpoints, so stereo 1A and L1, and versus just having L1 viewpoint, had a clear difference in arrival time error in CME. So it's about 2 hours in here. Also, if you actually quote the person, George Millward, who implemented the cone model in a space weather embryo model, said that it's actually hard for space weather forecasters to use single viewpoint image in a forecasting model. So it is highly problematic in many real world situations. You need at least 2 viewpoints to make a good prediction. So that is the conclusion. Having multiple space-based chronographs and continuing to have it is essential in today's space weather forecasting. And another thing is that this is going to be a first operational effort for the chronographs. So this is going to give you the earliest possible notice of impeding geomagnetic activity, thus providing the longest possible lead time for geomagnetic storm watches. And I think that has some contribution when you're thinking about society's resiliency to space weather. So it's like, if you see the CME in the field of view, that's the earliest signal. So this much time is, the best time you have to prepare your industries for what comes next and so on. So actually, that's the end of my slides, and just a little flyer that we're actually hiring. SEACOR team is looking for a new member to come in. So if you're interested in, please contact our PI. I'm sorry. Wow, housekeeping. Yeah, so we're hiring, and please contact Arnaud Tringien, who is our PI, or you can come talk to me. I have some handouts, printouts for the job description. So. Thank you for your attention. Yeah, okay, sure.
Okay, so the next speaker is Daniel Gass.
Thank you. Okay. Hi, everyone. Happy Halloween. I don't have a costume here, but Andres had a dinosaur that he was going to wear. Unfortunately, it has not made an appearance today. I'm here representing actually a part of a wider team, the FDL team. I'm the first one of the team, so I'm glad to make that introduction. So the title of my talk today is AIA is all you need. STO makes A and B virtualization via convolutional deep learning. As we may find out later, there are caveats to that statement, but I'm just going to present it as is. There we go. Yep. So Team FDL really was sort of a team effort, multidisciplinary. I'm the first one today, but Vishal is going up after me, so I'm going to hopefully leave him enough time to talk as much as he needs to. Oh yes, that's Frontier Development Labs, and so that's an effort between NVIDIA, NASA, and Google. And so these people have pooled together their expertise and their resources to help us tackle problems related to sort of solar data, especially machine learning tasks. And if you're recommending doing it next year, I'd highly recommend it. But to get on to the talk, yeah. So I'm aware most of the people in attendance will know what the Solar Dynamics Observatory is, but in the spirit of cross-disciplinary efforts, I'm going to describe where the data we use comes from. So SDO is the Solar Dynamics Observatory. It consists of the Atmospheric Imaging Assembly, which is where you get all of our nice EUV images in 10 channels, 496 by 496. We have the HMI, the Helioseismic and Magnetic Imager. And the thing that is of interest to us today especially is the Extreme Ultraviolet Variability Experiment, the EVE, which helps us measure sort of EUV irradiance, which, as we've known from a lot of these previous talks, is very important when we want to understand impacts for space weather. So to diverge a little bit, because this is really a talk about what we've done with the platform that we've built. So the motivation behind building that platform in the first place is that the SDO is a fantastic product. It has a lot of data that's available across sort of solar cycle 24. It was launched in 2010. But if you want to use it for a machine learning purpose, if you want to really exploit the data and use it in that capacity, it can be a bit of hard work. The SDO now has sort of order of magnitude around 20 petabytes of data. That's a lot, even with Google's help. We ran into a lot of issues getting that sorted, but we think that scientists need access to curated data. You can see there, that's sort of an example of some of the data you might encounter. You've got to fix that. So what we did is we helped build a sort of an automated pipeline to prepare and serve that data. I'm going to detail more about that at the end of the talk, but this is just a bit of a spoiler for a talk that I'm also giving tomorrow for a colleague that can't make it, but we have the SDO machine learning data set, the SDO ML, which has been sort of prepared for use for the 512 by 512 resolution. So a lot of sort of neural network architectures make use of images in that format. We've gone through the calibration, the validation, all the difficult stuff. That's part of what we did as part of FDL. But what we did with it is EVE instrument virtualization. That was sort of the task that we set for ourselves. And when I say EVE instrument virtualization, what I mean is using data from another part of sort of instrument virtualization. Basically, we use data from one part of the satellite to reproduce data from another part of the satellite. And the motivation for trying this in this case is that, unfortunately, the MEGS-A component, so the part of the wavelength spectrum there that you see it's been blocked out there, was damaged and rendered unusable in 2014, which means that if you want to get that irradiance data after 2014, you are unfortunately out of luck. MEGS-B also suffered degradation, can't operate at the same cadence that it used to. So what is it we're trying to do? We wanted to see if perhaps some of the fundamental physics that makes up the irradiance prediction that we see in the MEGS A and B could perhaps be captured by wavelengths of AIA that covered the same wavelength spectrum. So that was our sort of hypothesis. This has already been done in 2018. So essentially, we wanted to see if we could use a machine learning method to try and recreate the output of MEGS from AIA. What we find is that, yes, we can. In the large majority of cases for the MEGS A and B ions, we get pretty good results. We think that's because the sort of the wavelengths are overlapping with the irradiance. There are some instances in that it doesn't work quite so well, but in the majority of cases, we're getting to sort of within 10% agreement in the range of 2014. We used a sort of combination hybrid model. So that's a linear regression model that is then sort of corrected by a CNN model. And sort of one of the results that we got out of this attempting to perform this experiment is that we included AIA and HMI results, but we found that the HMI results actually were not necessary, and if used alone, were actually less useful than just AIA by themselves. As I said before, there are some caveats to that, so perhaps we could discuss that a little bit at the end. But this is an example of one of the ions, Fe20. So we see that the recreation, sort of in blue there, that's the predicted versus the observed throughout that period, ties pretty closely together. There are some periods during sort of peaks of irradiance where it doesn't match quite so well, but the mean error overall for the irradiance was 3.21%. In the spirit of open science, though, I also wanted to go over a result where things may be a little bit slightly off. This isn't a perfect result yet. We're hoping to improve this in future iterations, but we found that for some of the ions, especially ions that were not neatly covered by AIA wavelengths, that there might be some offset. This one here, magnesium-9, there was a mean error of about 5%, and it was sort of offset to be too high. But apart from that, we've been hosting the data here. I hope everyone can see that. But part of the results that we wanted to get out there and really sort of embrace the open science aspect of the challenge is that we've sort of put our results out on this platform, the SDOMLdemo.org. This was made by the very talented Richard Galvez, if you've ever met him. He's very good at this sort of thing. And so we have hosted a lot of the data that we have produced here. The model is capable of live inference, but at the moment it is somewhat restricted to the range of 2020 for this website. But we are hoping to resolve that in the near future and get these results out published soon. So our results that we've presented here is that the virtual Eve is a deep learning model that we have fed AI input data with the intention of reproducing output from a damaged instrument that we would otherwise not be able to receive any data from. We have hopefully shown that this method can potentially be used if another instrument in a similar situation can be damaged. Well, if it is damaged, we want to reproduce the results. The results are available for inspection download at sdmldemo.org. And we're going to get a paper out on this pretty soon if you want to interrogate some of the details further. I'm also open for questions, and I'm happy to pass questions over to the rest of the team. The open science question that remains is that, yeah, okay, HMI wasn't so useful in this case, but perhaps that was due to the infrastructure that we used. We had to feed in images at that 512 by 512 resolution. Perhaps if we used a different infrastructure or develop one ourselves that could take in higher resolutions, would HMI become more useful to us? Now, with the ions that we struggled to predict, what factors could we use perhaps to improve the prediction? And which AIA channels, this is like sort of ablative studies here, which AIA channels are really the most important for reproducing that irradiance output? What implications does that have to some of the more fundamental questions about how physics drives these irradiance measurements? That is all. Thank you, everyone.
Thank you. And the next speaker is Vishal Upendran. Yeah.
You got my name correct? Yes. Yeah. Hello, everybody. I am Vishal. I am a postdoc at Lockheed Martin and at Berry. And I was also a faculty at FDL this year. And as Dan has already given a very nice introduction, I don't speak just for myself, but for a lot of people. That's my team right there. I was leading this team with Bashi and Angelos. And I'm also thankful to the FDL 2020 team because we built this whole setup on top of that model which we had. So going in, we have seen a lot, or we have been hearing for the past day and a half on the effects of solar wind forcing solar activity on the Earth. So our focus in this whole work is to have some form of a model which is able to generate forecasts of, the end goal is to have a GIC forecasting setup, but we'll get there. We first start with what we call a global geomagnetic perturbation forecasting scheme. And what do stakeholders need? Stakeholders need a model that's fast, computationally it should be fast. it should be localized. Like you have these global effects that's happening everywhere, but you also have localized enhancements. So we need both fast models, we need them to give localized forecasts, and we need them to be actionable. And that was a very important point raised in the morning session, that the stakeholders need forecasts which are a week in advance. And I'd say a week is a lot in advance. That's probably a bit difficult, but we can go a couple of days in advance. So this is Dagger. It's a geomatic perturbation forecasting model. What this does is it takes in the Omni measurements at L1 and folds them through a fancy AI model and is able to generate. Do I have the laser pointer? Yes. And it's able to generate geomatic perturbation forecasting across almost the whole globe. This was FDL 2020. And we wanted to increase the TRL, the technical readiness level of this model, and also have the increased read time. So what do? We come up with what's called adaptive forecast refinement. So we were actually inspired by what's called the adaptive mesh refinement that occurs in numerical simulations, where you have some big, let's say you have a shock or something that's happening, and you have much finer grids as you keep going down and down. So what we did is, okay, the system is actually twofold. You have something that's happening on the sun. You want to get a forecast at L1, let's say, or of the solar wind and IMF many days in advance, and then use that to drive the existing Dagger model. That's actually what we want. So we developed what's called Sheath, which is a model that gives us these forecasts of solar wind and IMF, given the SDO-ML dataset, which Dan talked about. And we have the Dagger++ model, which is basically also incorporating the state of the magnetosphere in some sense. And magnetosphere itself has some memory. It's not just a solar wind forcing that's giving rise to whatever perturbations you see on the ground. So we have what's called the Dagger++. So the way this works is Sheath gives you a forecast of solar wind measurements. You feed that to Dagger, and you get a forewarning a couple of days in advance on what these perturbations would be like. When you get Omni data, it's going to go into Dagger++, and you get a much, much better forecast of what these geometric perturbations are. So that's not going to details. This is what a model scheme looks like. We basically came up with a feature generation scheme where we are segmenting out kernel holes and active regions and considering the intensities and magnetic fluxes within these regions from SDO-ML. We use that to train a solar wind regressor and generate proxy solar wind and IMF measurements. That goes into a Dagger model, which basically summarizes this time series of solar wind and IMF measurements and decomposes this summary state into spherical harmonics and generate these forecasts. So what do we have? So this is Sheath, and this was a joint event all of us team studied during the FDLX this year. This storm was caused because of a high-speed enhancement. And you have the SDO AI and HMI data that's running around. You get a set of forecasts like these. These forecasts are then fed into Dagger, which give you perturbation measurements in horizontal and the northward component like this. So these are some statistics here. The blue curve is the actual measured Omni measurements, whereas the orange is the forecast from our scheme. And we were actually very, very surprised to see this very nice match in solar wind speed. But if you go and read papers on solar wind coming from kernel holes, you actually would expect a very good match. And that's really captured very well by the model. And on Dagger++, once we have the solar wind measurements from Omni, we identified a couple of regions where we need to have some work done. And we know that the data set actually is imbalanced. Storms don't occur all the time. And the sampling in space of these perturbation measurements is also not uniform. So you need to account for all of these imbalances. So we perform multiple experiments where you basically correct the loss function depending on whether the sample comes from a storm time or not. That's called imbalance correction. Then we include the geometric indices as a proxy for the state of magnetosphere. And finally, we have what's called ground station regularization, which was very fancy because if there are a cluster of stations seeing the same measurement, you are much more confident that this is actually a real measurement and it's not just some noise factor. That's basically what we do, and we just correct the loss function. So yeah, so a couple of works. So this is ongoing, right? So we had like initial model, initial setup done as a part of FDL, but we need to look at aviation studies, perform benchmark studies and stuff like that. And that's what the team is working on right now. So this is with station regularization, where you can see that we are actually over-forecasting, over-predicting a lot of these measurements, which gets better actually with imbalanced regression if you just add them with indices. So it's a combination of all of these different error terms that play together to give you a good model. So what we also have is ensemble modeling. So we are able to generate uncertainties, and so we know whether how confident we are of a given forecast. And that is rather very, very important for any forecasting scheme that anybody is developing anywhere. So yeah, so that's sheath and dagger. Because we had named the model as dagger, we call this other model as sheath. And so also supposed to represent the magnet of sheath or something. So yeah, it's a bad play on words. So we have sheath and dagger, which we are benchmarking and training on around 12 years of data from SDO-ML and looking at feature generation. So we also have ranking of features, for instance, from AIA and HMI to see which are probably important. So that I think is rather very cool, and the team is working on this. So I just stop there. Thank you. Thank you.
Okay, then thanks for keeping in time. Great, it's great. So the last talk of this session is from Azziz Diaby.
Okay. Hello, everyone. My name is Azziz Diaby. I come from Ivory Coast in West Africa. And my work is about the estimation of the daytime vertical E-cross-B drift velocities in the equatorial F region ionosphere using magnetic data. And this is the name of my laboratory, but it's in French because we speak French in my country. So, next. Yeah. Oh. Okay. Plasma vertical drift velocities has become an important parameter for different processes that dominate the equatorial ionosphere, such as equatorial electrojets, equatorial ionization anomaly, and diverse plasma instabilities. The equatorial ionization anomaly consists of two crests of high electron densities around 20 degrees plus or minus 20 degrees north of magnetic latitude. The primary mechanism for creating this anomaly is the vertical drift velocities. So, despite this importance, there is a lack of instruments over African region that are able to directly measure vertical drift in our region, which motivates the development of various methods to derive it. In this work, we use the method of Anderson et al. In 2004 to calculate the vertical drift velocities. In the work of Anderson et al., it says that the H field measurement from a pair magnetometer station near deep equator and another located at 6 or 9 of deep equator provide an estimate of the EEG and thus the daytime E-cross-B drift velocities. So they establish an empirical drift velocity formula as shown below. So in this formula, we have many parameters that like the day of years, F10.7, F10.7A, KEP, local time, but the most important parameter is delta H. So this relationship was suggested to be applicable to all equatorial latitude. So in this work, we use data from Sikasso, Lamto, and Tombouctou that are part of the International Equatorial Electrojet Years in 1993. And the second set of data is the data from the AMBER, the African Meridian Bfield Education and Research Network. We use data from Conakry at the deep equator and Abidjan, 6 degree out of EEG influence. So first we calculated H0, the nighttime baseline for each day, and then subtract to H to give daytime value. This produce daytime H component at each station. So now we calculated delta H ST, which is delta H, taking account the station of Sikasso, and that's of Tombouctou. Delta H Sikasso, delta H AS and L is delta H calculated using the pair of station Sikasso and the station of Lamto. And delta HCA is delta H obtained using the pair Conakry and Abidjan. And on this plot, we show the derivation of the EEG magnetic effects. The red one is H at Conakry. Conakry is located at the magnetic equator, and Abidjan in blue, H Abidjan in blue is located out of the EEG influence. The black one is the difference between the H component at Conakry and the H component at Abidjan. So here we can see that H at the magnetic equator is important than those out of the EEG influence region. And in the early morning, you can see a depression that is due to a equatorial electrojet. And this plot shows the diurnal variation of EEG and its related drift velocities. So on this plot, the red one is delta H with respect to Sikasso Tombouctou, and the blue one is delta H with respect to Sikasso Lamto. And on this one, VD is the vertical drift calculated using Anderson formula, but taking account the station of Sikasso Tombouctou, and VD SL is calculated using delta H Sikasso Lamto. And we can see that those curves have the same evolution. So we can see that on delta H Sikasso Tombouctou is higher than delta H calculated using delta H Sikasso Lamto. And this is same we can notice on the vertical drift velocities. This is normal because the formula is very dependent of delta H. And we can return that delta H Sikasso Lamto, H Sikasso Lamto latitudinal separation is about 6.18 latitude, while Sikasso Tombouctou is 6.64 degree latitude. And we can conclude that the value of delta H Sikasso Tombouctou and its corresponding vertical drift are slightly higher than those of delta H Sikasso Lamto and its related vertical drift. This is normal because Lamto is near the Sikasso station. And the pair with the largest latitudinal separation exhibit the strongest EEG, while we want with smallest latitudinal separation present the weakest EEG. Thank you.
Thank you. So if all the speakers could come up to the front, we'll have a Q&A session. I'd like to ask this. Oh.
4 people.
I have a question for Daniel. Yeah, first, very nice presentations and work.
Thank you.
And you showed one slide about magnesium 2 prediction or forecast is a little bit off.
Yeah.
So I think the reason is the 1600 and 1700 line. We don't have a good correction for the degradation. We are underestimate the degradation. So this is a known issue that we are working on that. And so I think that probably explains the offset. So maybe you can use other lines to exclude these 2 lines and retrain the model, see if that can improve. So we have a fairly good degradation correction for the EOV lines, but for the UV lines, we're still working on it.
That's a good point. One of the next steps that we wanted to do as part of that study is to work out which lines we didn't need. Perhaps there were lines that were making the prediction worse. So as you said, there's good reasons to suspect that maybe the sort of the 1600, 1500 lines were sort of making things worse there. So I think that's a good next step.
And because the formation height is directly related to magazines too. So
yeah,
I think that's probably.
Yeah, we basically just included it for completion because we could. And so the next step was once you've used everything, work out what you actually need and maybe refine it more and make it better.
I'm just to follow up, I'm fascinated by this idea of a virtual instrument. So how will you flag this so that someone doesn't come along and think, oh, this was actual real data?
We definitely don't want to represent it as real data. It's not something that is a replacement for a real instrument. It's just that in that instance, we're never going to get another instrument to perform that ever again. So in that case, it's better to have something than nothing. I think that if we could get something that could perform the same way, that'd be also be pretty good.
First, I want to make a cheeky response, and this is Daniel, your presentation. So we didn't have to send an astronaut to Hubble to fix Hubble. We hired, AI and domain experts to fix our problem. That's what we do. And what's the difference between virtual and reality if they look the same? So that's amazing, and they are continuing to make progress. So imagine these kids are doing the work in 8 weeks of summertime. And this is ongoing work. This is pretty amazing. So people who are afraid of AI ML, I say AI is not artificial intelligence, it's augmented intelligence. It's just like telescopes, microscopes, any of those. We are enhancing our intelligence by using mathematical tools. So if you use it right, there is so much benefit to be had. But all of you, excellent presentations, all of you. Thank you.
But I'm assuming you have metadata in your data set that sort of flags it, right?
Yeah, we're not presenting it as real data.
So maybe this is sort of a tongue-in-cheek or provocative question, maybe for Lika. So we've heard presentations on virtual instruments and real instruments, and even this morning a real mission, right, from Craig DeForest. So if we can generate all this wonderful data for a virtual instrument, why do we need real instruments?
Well, virtual is built on the hide of real. So if we didn't have AIA, we wouldn't have virtual MEG, but we are creating a different kind of response function from something else. It's incredible what we can do. We can calibrate instruments actually without underflying rockets. And I know Greg is not happy probably to hear that. He's shaking his head. But these are things we have to try, Greg, and see how well it.
Your example with Hubble, CoStar wouldn't have worked at all.
Lots of things wouldn't and lots of things do. So we have to try, right? We have to work that space and not dismiss it offhand.
This is a wonderful backup, given that the instrument failed.
Yes.
But it would not be the original instrument.
Absolutely not.
Flown.
You done? You good? Okay. Question for Vishal first, and then Daniel. So Vishal, you presented on a pair of models, I think trio of models, if I followed correctly. Can anyone in the community access and run those models for themselves, or is it running in real time somewhere?
Oh, no, it's all on GitHub. So the Dagger model is actually online. I was showing this yesterday in the working group. The Dagger model is on what's called SpaceML. SpaceML is a repository of all of the FDL projects we do, and you can access them as Colab notebooks. You just open it up and just run it online. You don't need to install anything on your laptop or your system. That's Dagger. Dagger++, the hyperparameter optimization is not done yet. So we are still, so once we finish all that, once we write our papers and get them out, we'll make them public. And that's something I will die on that hill that we'll make it public. So yeah.
Thanks. Question for Daniel. You know this is coming. So the SDO-ML data set has been through a few iterations. It will probably go through more, but I think at any iteration it's important to preserve that progress permanently. I saw the data set being available through an interface, but what are the plans for permanently archiving and preserving that progress?
We are currently working that out. So that is definitely something that we want to be doing, but we're just trying to work through what the best solution is for the most people who might be interested in that particular version of the data set. Yeah.
More questions? Okay.
I have a question for my brother Azziz. In your study of the vertical drift,
Yes.
you used a Dawson model, and you presented 3 magnetometers results.
Okay.
Did you use the magnetometer results to look at the asymmetry of the EIE structure in terms of whether it is within the northern hemisphere or southern hemisphere, which one is larger? And secondly, the data you presented do represent the same solar cycle or 2 different solar cycles? Thank you.
Okay. I did not do, I haven't do this comparison. This is another work I'm doing. And for comparison with between solar cycle, it is included in the work, but I didn't present it because I had only 10 minutes. So I can show you the paper if you want.
Everyone's a bit quiet. All right. No more questions. We'll have a coffee break. Thank you. Thanks.
Yeah, I mean, and also there's Also, like hydrogen bring those ions. Yeah, and the space preparation mix of other species. You know, there's no point either go to such a high altitude, so nobody So one of the assumptions they but they also So to do that, I kind of have the assumption that let's forget about let's assume they can for some reason they're going to 7 hours for duration. So I give and then I and how does So there was this aspect. And it's not unless yeah, they have to reach 1,000 altitude. Once they get there, they will fall. Yeah, so I did so I would say if they can get it, like these they will definitely.
What is the biggest temperature? So, because steel has it's sorry. Because yeah, actually, what is but I just very I don't want to challenge. I just assume that they can based on my because I have no idea how this is. So strong candidate. So looks like there's yeah, but I really need some people that know what's going on below I can try my best to send them up. Do you have any validation observation? Yeah, right. Yeah, that's what I. Yeah. So how is the longest of Metallica index? Is it available? Yeah. I think there's something out of that would be good, so at least I can say this is. I also want curious. What is the difference between like I'm pretty sure there's physics do they follow the same trend or different trend? So right now I just say we can give this right now to that That's another, yeah. So the model I have focused on, so we are so they do have so that's another possibility. So that's another thing, like because paper structure. So probably yeah. So the model so that's why I say there's so I have no idea. Yeah. Yeah, I mean, it's a start. But I will be very interested in I mean, just yeah, I mean, just like if you don't know. Yeah, and I still don't know the answers to this question. Yeah, but I'm not talking about this. Your model doing better than oh yeah, that's I know how to first take a look at it. So appreciated. Especially about yeah. That makes a lot of vision because they don't think metallic. How do you know? Because their hands is so that would be an interesting story to see. I think nobody knows. I'm excited. I still don't know. It's like a question mark. Question mark. So I read
Well, it gets forward.
Is this working?
Testing, testing. Oh, hey.
Okay. Do we have more people outside? Hi all. I think we are going to get started in just about a minute or two. Please take your seat. Just making sure everyone who is here is in the room and not in the lobby. Okay? Okay. Give it a minute. So we have two more talks in the afternoon, followed by an hour of working group discussion, like we had yesterday. And I guess the working groups are they going to be divided up again? Same situation will be arranged. There'll be two rooms parallel here, side by side, and the third one upstairs. I think everyone is here, so we are going to get started. These are the last two talks of today's session. And this talk is this is a student speaker presentation. This is by Kalpesh Ghag from Department of Physics, University of Mumbai. And he's going to talk about ICME-driven geoeffectiveness insights from planar magnetic structures.
Hello. Sorry. Finally, I'm here after one visa rejection, flight cancellation, and oh no, kid had known my old sad stories. So probably I'm studying. Myself, Kalpesh Ghag from Department of Physics, University of Mumbai. On 13th March 1989, the people from Quebec experienced a scary winter night with 8-hour blackout. And I should skip this all because we all know from the last 2 days about space weather disruption with all power grids, then GPS systems as well as satellites. So until now, we know that the geomagnetic storm is one of the candidates for such geomagnetic disturbances, and it is actually shown as a proxy by the C-match index, where it is a temporary disturbance to our geomagnetic field. And what is the physical mechanism behind it? When the southward component of the magnetic field come towards our northward component of the magnetosphere, and when it reconnects, then we get some ring current enhancement, and due to which we observe such geomagnetic disturbance. And these are the main phase. So this is called as initial phase of the storm, this is main phase, and this is called as a recovery phase of the storm. So who carries this southward magnetic field? The ICMEs. This is a image of the SOHO spacecraft from the remote sensing observation, and how we all in situ people sees this ICME in interplanetary space, like some shock, then there's turbulent sheath, then there is a magnetic cloud. So it depicts in such observations of magnetic field parameter as well as plasma parameters. So this ICME do not swim alone in a sea of solar wind. It constantly interacts with the other ICMEs with preceding solar wind. So due to that, it may get deformed, it may kink, rotate, and all such cases, and sometimes it may get pancake. Our group observed that with the interaction of the solar wind, the ICME's magnetic cloud get pancake. So if you see here, this is a typical cross section of uninteracted magnetic cloud, and if you see, this is typical cross section. It is elliptical cross section of that pancake magnetic cloud. Uh, I'm depicting it as a compression of that particular magnetic cloud, and if you see here, it shows certain relations, certain model field. This is the color scatter plot is the data, and this black line is some model fit, and this model fit is for the PMS, that is planar magnetic structure. We observed that when this ICME get interacted with the solar wind as well as ICME, it ICME magnetic cloud transformed into some structure called as planar magnetic structure. So what is PMS? PMS are the structure where the interplanetary magnetic fields are constrained into some planes. So here you see these are the identification criteria described by Nakagawa and Parmerio et al. You see here these PMS are unknown. PMS are known for solar wind, that is in co-rotating interaction region in ICME sheath. People have observed it in ICME sheath. People have observed this PMS in a magneto sheath also, and our group has observed these PMSs in magnetic cloud. So there is quite debate about this, because if you see this structure of the magnetic cloud in situ parameter, people says that the rotation of such elevation and azimuthal angle is usual. But our group has also found that this PMS is not for all magnetic cloud. Those are special magnetic cloud which get transformed into such planar magnetic structures. So Sheikh et al. 2020 statistically studies these ICMEs and found that 35% of ICMEs sheath are transferred into this PMS, that is planar magnetic structures, and 29% of ICME magnetic cloud get transformed into this planar magnetic structure. So these are typical plasma property as well as magnetic properties, magnetic field property of this ICME. If you see for the non-planar case and for the planar case, these typical parameters get significantly enhanced. For example, let's see about BZ. BZ is a main candidate for the geo-effectiveness of the geomagnetic storm. So if you see here, it is minus 6.91, but for the ICME planar sheath, it is about minus 15.43. Same about ICME magnetic cloud. If you see here, it is minus 9.46. For the planar cloud, it is minus 13.67. Number density is also for the same. So we observe that these parameters that are affecting for the geomagnetic storm are get quite enhanced due to this PMS. So we studied one case where this PMS transform magnetic cloud, if it encounters our magnetosphere, it causes extreme geomagnetic storm, and we thought that let's try for statistically. So we statistically studied this type of events, and we categorize all the ICMEs into these 4 categories, that is planar, non-planar structures, planar sheath, planar cloud, as well as planar ICMEs. And we noted the C-match value in each case. So for planar sheath, the value for C-match high and C-match low. For planar magnetic cloud, the value for C-match high and C-match low. And for planar ICME, where both sheath as well as magnetic cloud get transformed into this PMS structure, we noted the value of high and low C-match index. And we plotted this, and we get this confusing statistical result. Let me explain. For left side, if you see, this is a distribution for the C-match high value. So this is for the initial phase of the geomagnetic storm, the amplitude of the initial phase. And if you see this right column, then it shows the amplitude of the main phase. First row indicates the all data for the non-planar ICMEs, second row for the planar magnetic cloud, third for the planar sheath, and fourth for the planar ICME, where both sheath as well as cloud transform into PMS. And if you see here, the mean values of all distribution for the non-planar ICMEs, it is about minus 57 nanotesla, but for the planar cloud, it is minus 71. For planar sheath, minus 58, and for the planar ICMEs, it is about minus 98 nanotesla. So it is significantly enhanced. For the for the initial phase, let's see the mean value for that is 10 nanotesla, and if you see here for planar ICMEs, it is about 31 nanotesla. So we see that the geo-effectiveness is quite high in the case of planar ICMEs. And here, if you see, if you divide all the storms into extreme, intense, moderate, and weak, you will see that for the extreme storm, the candidates are planar ICMEs. They are major candidates. And for the non-planar ICMEs, we see there are only 0.48% storms that are extreme geomagnetic storm. Similarly, the relation holds for the intense storm also. So what are our major findings? So our study statistically confirms that the ICMEs which transform into PMS are more geo-effective than the non-planar ICMEs. So the combined effect of the enhanced magnetic field as well as the plasma parameter is contributing into such high geo-effectiveness. So what's next? I think all we know that the extreme geomagnetic storms are due to sheath, but at what degree planarity enhances the that geo-effectiveness that we really want to study? Then everyone is talking about minus BZ, that is southward magnetic component, and main phase of the storm. But we noted that during such initial encounter, when this BZ turns northward, it significantly compresses our magnetosphere, and sometimes the magnetopause boundary goes up to 6 RE, and it exposes our geosynchronous satellite. So we thought that it is important to study that initial phase of storm. It is also important. Then the contribution of such PMSs into ionosphere and magnetosphere coupling, we are also interested in that. And we encourage all the modeling and the simulation people who are working in geomagnetic storm to take consideration of this PMS effect, because these are the major candidate of this high geo-effectiveness. And then about how this PMS accelerates the particle and all that, we are quite interested. So these are the typical publications, list of publications which are regarding these topics. What we are doing, my colleague Omkar actually has explained what we are doing in Department of Physics regarding the context of heliophysics. And thank you.
Questions together after the next talk. So our next talk is by Souvik Roy from Indian Institute of Science, Education and Research, Kolkata. And the topic is Advancing Space Weather Understanding, Deciphering Geomagnetic Storm Drivers Through Stormy Simulated?
Yes.
Okay.
Kalpesh, for me, visa was rejected 4 times. And I got my visa after flying half of the country on the very last date. But I'm still find it difficult which one was tougher for me, the visa case or making a 10-minute presentation of my 3 years of research. Let's see how I have done, well or bad. So let's start. I'll make things simpler and brief. If you want to know about the complexities, catch me after this talk or tomorrow or day after tomorrow. So let's start with the context. Context is very simple. A CME is coming and passing the Earth. We have data at L1, we have satellites, and using that data, we are modeling a 3D structure of the CME. So a typical 3D structure with latitudinal, longitude information, magnetic information, twist information, and then we are using a computational model with that 3D CME and Earth's dipolar magnetic field and interacting them. And what we are getting is this, the video. So as of now, this is solar wind driven magnetosphere, the typical textbook image. You will very soon see the CME impact on this magnetosphere. Yes, you see things are now very difficult to recognize. Okay, it's not the very textbook image anymore. And our main aim is not to create these fancy videos to do the science. So from this, we'll try to get the DST. So let's start. Oh, this is the Stormy. I forgot to introduce. We call this module Storm Interaction Module, in short, Stormy. So the approach that we are taking. The approach is very simple. You have to deal with plasma in a large-scale computational box. So MHD. We are modeling our own Earth, giving it a magnetic field, modeling our own ambient for the Earth, solar wind, and the CME that I have already talked about, and using Pluto. Pluto is an open source MHD solver, and asking Pluto to solve the MHD for us in each grid point. I'm not going to bore you with all the assumptions, but as on the left side cartoon, you can see that we are very much focused on the planet itself. The star is far away from us, so we don't bother about the impact back on the star. Particularly for Earth, I don't think there is any. Anyway, so now let's move to result, and I'm going to spend some time here. First, I already showed you the main video, so I'm not going to repeat that, but this one is important. I'm going to point this side, if you guys can look at this side. On your left, what you are getting is equatorial plane from our simulation. Earth is at the center. On the right is the theoretical understanding of the current system within the magnetosphere. So you get ring current and magnetopause current, and if you can see, you'll see that we are getting similar behavior of currents in our simulation. Now I'll pause here a moment. When we talk about current in plasma physics, it creates confusion. Why? Because we are not dealing with any particle description of plasma, any PIC, any kinetic description of plasma. This is pure resistive MHD. This current that I'm showing is induced current coming from curl of B. And it's the very beautiful nature of the physics that because of the topology, we can match the typical current direction on the equatorial plane. And now if I play this video, you can see when the CME hits, there is current enhancement. There is current enhancement on the night side as well as day side. And there is asymmetry also, and things change. So we thought, why don't we use this ring current to calculate DST? Now, those who are not familiar with DST, I'll just take 2 minutes. So what happens is, in reality, the ring current gets enhanced during storms. So ring current the term ring current is not correct. Ring currents, it's a bigger umbrella. So ring current flows in a way that it tries to minimize Earth's magnetic field. When there is a storm, ring current enhances, it minimizes the Earth's magnetic field more. So if you put a magnetometer on the equatorial region, on the equatorial region, you'll see that during storm, your horizontal magnetic field has decreased. So from a quiet time value, if you calculate how much decrease is got and then do some calculation, you'll get DST. That's the very layman's way of describing DST, but this is true. Now, if we use Biot-Savart law on this current that we are getting from our simulation, and then do some calibration. Don't ask me about the calibration. It will take another 10 minutes talk. Ask me later. I'll describe. And we get a very good Pearson value. The predicted DST from our simulation and the real DST that we get in real life, they are very much correlated. I can only show you 2 results from an extreme event and a moderate event, but we have done this for 15 different type of CMEs of different orientation. Those results will be published soon, and then I can share those results with you. But this is not only about the DST index. Let's look at the magnetotail. On your left, you're getting a magnetotail theta-shaped current from simulation. On your right, what you are seeing is the observation by geotail of the same current system. They are very much similar. Now, if I play the video, you see how CME impacts the magnetotail. You see this dance, this movement? This is because the incoming magnetic field of the CME, some components are changing polarity, either BX or either BY or BZ. Because of that, the magnetotail show this kind of a shift. And if you think about it, the movement takes time to go further and further away in the magnetotail. So there is ultimately a torsion that is created within the magnetotail. That's not all. We can also give you an estimate of joule heating. From the J square, we cannot give you value in gigawatt because we are not incorporating ionosphere. So no conductivity incorporated, but from typical J square, the joule heating, which is, the proportional to, we can give you an qualitative idea that how much percentage of increase we can expect. And we have checked with SWMF and TIE-GCM. In those cases, our values actually very well correlated. Now, I'll stop here with the results and let's move to the ultimate goal. Now, before you ask me this question, I'm going to answer you this. Are we predicting DST or CMH? They are de facto twins, not exactly the same, but one is 1 hour cadence, one is 1 minute cadence. The big background physics is more or less same. So are we predicting this? Technically, no. Because as I already told you, whatever I got, I have not used any particle definition of plasma or ring current physics. So if I call it a DST, it will be biryani without rice. Okay, but as a proxy of DST, what we are getting is giving us a good estimation of the geoeffectiveness. And this is, for us, is a balance between complexity in modeling and achieving efficiency. With that, if I now ask, so with the proxy of DST, can we do a real-time prediction? Like there is a CME, can we, at L1 point, can we do a real-time prediction? Unfortunately, no. Because a simulation takes around 2 days to 7 days to run. I have access to 144 core HPC. It's impossible. And it takes 60 minutes for ICME to reach Earth from L1 point. So I'm running against time. Again, there is a but, and the but is it's not actually impossible. Either I have to arrange funding and buy a extremely high power HPC, or I have to remove dependency on L1. So you give me a predicted flux rope structure at L1. Look at the sun, you see a CME coming to us. Use your analytical method, use your MHD method, use your empirical method, I don't care. You have to give me what flux rope you are expecting at L1. Tell me, Souvik, I am expecting B0, the axial magnetic field to be this, orientation to be that, radius to be that, and I can give you not only a proxy of DST, but also how the magnetosphere you can expect, how the magnetotail you can expect, where you can expect currents, and that's, even the joule heating enhancement you can expect for that storm. So that's not all. There are other possibilities. Now with this, we can look at CME-driven space weather for exoplanetary world and actually validate observations. I am planning to incorporate ionosphere and thermosphere as well. For thermosphere, I need 2 fluid MHD into the model so that I can make the result more robust. So, and also increase the computational efficiency. So anything, if you want to suggest that I can do, please, you guys are welcome. So I'm looking for collaboration, and I am also looking for postdoc opportunities. If you think that I can join you, or you can help me, or we both can write to the the Jack Eddy fellowship, I'm happy to do that. Just let me know. This is the paper that I discussed in this topic, and this is my mail ID. Those who are not here, if you are watching me online, this is my mail ID for further contacting me. And thank you. And a personal mention to Kate, to Lika ma'am, to Cindy, to Lucas, to Sarah, and all those who actually managed to get me here on the very last day. I had to fly across the country, then again come back to Delhi. Faster than a CME, that's true. But the back-end support from here was awesome. Thank you guys.
So questions? Well, you have to have some questions.
Either I gave it too good or too bad.
Sorry?
Either I gave a too good presentation or too bad presentation. Thank you.
So I have a question for you about the STOMY model. So when you propagate the flux rope structure, so do you assume this is a self-similar expansion, so there's no interaction with the background solar wind? Is that the
for me, the left boundary within the domain starts from L1, ends on the other side at L1, L2. Within that, I assume that the flux rope is not expanding. Okay, so because the time frame is so less, it's interacting with Earth, considering the whole path it has traveled, since the interaction time is very low. For the benefit of the modeling thing, I initially considered that we shouldn't put expansion to it. But now as a version 2.0, we are planning to incorporate not only expansion of the flux rope, even Earth's magnetic field also rotates, because it takes almost one day to pass. In that one day, Earth's magnetic field do a rotation. We are trying to incorporate all those, making this model more explicit and robust in that case. So yeah, we are incorporating that, but for the time being, the flux rope is not expanding within the domain.
Okay, I see. Another question is more details about the one comparisons you showed.
Yeah.
That the index, the KP index were same H. Yeah, this one. So for both case, extreme and moderate, I see this STOMY index has this initial fluctuation.
Yes.
What causing that? Well, it's
so
not showing the.
You're talking about this particular.
Oh yeah.
So what happens is, in reality, you expect a storm sudden commencement. We are getting that, but after that, in plasma, the relaxation happens too fast, and it compresses and then relaxes.
Okay. Yeah.
Within that region, you get that peak, and that's for that small part only. It will, even if you zoom in here, with respect to this one, you'll also see there is a initial. That's because there is a shock. We are also incorporating Rankine-Hugner condition to place a shock in front of the CM.
Okay, I see. Okay.
So the shock is encompassing the whole magnetosphere and then relaxing within a fraction of a second. In computational time.
Okay.
So during that part, you expect that thing. That's like, how should I phrase? That's like using the typical MHD model to do this. We have to incorporate more robust, more ionospheric model or electrodynamic solver. Then we can get rid of that.
Okay. Oh, thank you, Souvik. Thank you very much.
Other questions? Yes.
So I'm probably going to show my own elementary understanding of modeling with this question. But I understand that when you add complexity to a model, you add runtime.
Yes.
It takes more time to run. So at some point, you're going to add enough complexity to this model that you can't predict it faster than it gets here.
True.
So there's been some work done. I've seen a presentation by Enrico Camporiali, if I'm saying his name correctly, about using machine learning to understand, not only to emulate some physics modules, forgive me, Daniel Marsh, if you're in the room, but to emulate some currently existing physics simulations to speed up code. They're doing that at for geospatial storms, but also to use ML to understand the differences and start minimizing that and decreasing that.
Okay.
is this a new idea to you, or were you already
No,
thinking about
the
this?
thing is, if you want to incorporate ML on top of this, then you have to have a data set. Then you have to run all the simulation, I mean, for different cases, past cases. Then, yeah, it can be done. Like it will be like additive effect on the results, I mean, if it helps.
Yeah, on that note, I think, are you talking about the Enrico's paper? I'm sorry, but is this the Enrico's paper with where he's doing this particle in cell simulations or something, or? Okay, because I read one paper where he does something similar, and that's basically using what's called physics-inspired neural networks. You're basically solving your MHD equations by factorizing or parameterizing your B's and all of your dependent variables as a neural network basis in space and time.
Okay.
So what you solve is basically you're minimizing for your MHD equations, or whatever your equation of choice is, and your initial condition in a boundary condition. So Enrico, I did read this one paper by Enrico where he was doing it for some particle-based simulations, which is very cool because he was looking at the distribution functions of different particles. It's a much simpler setup there. This setup is going to be much more complex, but
So can you share that paper with me? I think
sure, I can. We can talk. We can always talk. Yeah, yeah. Thank you.
Any other questions?
In your model simulation, you used SimH and DST index. So you did not look, you were referring to the geoeffectiveness of the Earth, looking at the ionospheric response.
Sorry?
I said you were looking at the geoeffectiveness of your model
Yes.
on the Earth's atmosphere. How do you characterize that geoeffectiveness? Because if we are looking at the ionosphere as an ionospheric physicist, we know that DST index alone does not give us a clear picture of how a geomagnetic storm impinges the Earth. We also have other criteria we have to look at.
See, let me tell you this honestly. When we started developing this model, we never thought that one day we'll predict DST. Things was like, let's put a CME into the domain. Let's see what's happened. We got current. We thought, okay, this current is matching the ring current profile. Let's try to get that if it can predict DST or not. That's the way we have came here. So to answer this, yes, there are different indices. I mean, you can try to predict other indices also. But for DST, the primary driver was ring current. And as we were getting something related to ring current, though I cannot call it ring current, it was for us the DST that we can predict using this.
Thank you.
Any other question? Any question for Kalpesh?
I want to ask Kalpesh.
Yes. You can ask right from there.
So Kalpesh, tell me, in a planar when a CME has a planar sheath, it does the the magnetic cloud also is planar? I mean, how can you say that the sheath is planar but the cloud is not?
So there are, as I explained, there are particular criteria for the magnetic field rotation. There are some analysis method. We have to just take a MVA analysis for that, and we see there is clear some sort of model that theta and phi should obey that scatter plot. So we have particularly studied the sheath independently, and we fit that model. If we are getting that perfectly fit for that sheath, so we are called it as a planar sheath. For the planar cloud, we try independently. If we see it, so then it is planar magnetic cloud. And if we get both for IC cloud as well as sheath, then we called it as a planar ICM.
I have a suggestion. Can you check that for all the planar sheath, you have a planar magnetic cloud or not? Because then it doesn't make sense to separate them.
Yeah, but sure, there are different mechanisms for all such both cases. For planar magnetic cloud, the magnetic cloud may get pancake and all such case. For planar sheath, the mechanism is different. There is a draping of magnetic field line due to such shock, and plasma pileup is there, and due to that, sheath get converted into planar structure. But yeah, it is fine that if the planar sheath is there, is it linked with the planar cloud also? It is one interesting net, and we can think about it. Thank you.
Well, thank you very much. I think we are about getting close to on the hour. And I don't know what the situation is. Do we take like 5 minutes break for the room to be divided up? There is about an hour, 4 to 5, to continue the group discussions that started yesterday.
Hi, everybody. So yeah, just give us 5 minutes, get a cup of coffee, please, and then we're going to divide the room, and they will be the same breakouts as they were yesterday with the same Zoom links, with the exception of the exoplanets. There's a new Zoom link for that, and it's in the Slack channel. Thank you.
This one doesn't work for that.